Hello there and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're heading somewhere very far away. Not to a planet, not to a galaxy, but to the edge of a giant cloud of gas and dust where new stars are quietly coming into existence. Before we begin, I'd love to know where in the world you're listening from tonight. Is it late evening, where you are? Early morning? Perhaps you're settling into bed after a long day, or maybe you're simply looking for a peaceful corner of the universe to spend some time in. If you find this journey soothing, interesting, or simply a pleasant way to unwind, I'd be very grateful if you gave the video a like and maybe subscribed as well. It helps this little community of curious sleepers continue to grow. Now, make yourself comfortable, let your shoulders relax, and allow your thoughts to slow down just a little. Because tonight, we're going to visit a mountain range unlike any found on Earth. There are no hikers there, no forests, no rivers, no snow-covered peaks. In fact, there isn't even any solid ground. Yet when humanity first saw it clearly, it looked uncannily familiar. Towering cliffs, jagged ridges, deep valleys, a vast landscape stretching into the distance. A mountain range carved not from rock, but from gas and dust. A place where stars are born. The region is known as the Cosmic Cliffs, and although it appears almost close enough to touch in photographs, it lies roughly 7,600 light-years away from Earth. That number is so large that our brains tend to treat it like background noise. 7,600 light-years. It's easy to say, much harder to picture. Light travels at about 300,000 kilometers every second. In a single second, it could circle Earth more than 7 times. By the time you finish listening to this sentence, light will have traveled millions of kilometers. Yet even at that incredible speed, a beam of light leaving the cosmic cliffs would spend 7,600 years crossing the darkness before arriving here. When that light began its journey, humans were still building some of the earliest civilizations. Ancient kingdoms rose and fell. Entire languages appeared and disappeared. Empires existed only in the future, and all that time, the light kept travelling, patiently, silently, crossing the enormous gulf between stars, eventually reaching a telescope orbiting high above Earth. And that's how we received one of the most extraordinary images ever captured. Interestingly, the cosmic cliffs are not actually cliffs at all. This may sound slightly disappointing. Astronomy has a habit of giving things dramatic names and then immediately explaining why those names aren't technically accurate. The North American Nebula isn't North America. Planetary nebulae have very little to do with planets, and the cosmic cliffs are not cliffs. Instead, what we're seeing is part of a massive star-forming region, known as the NGC 3324, located within the enormous Carina Nebula. The image became famous after it was released by the James Webb Space Telescope. Almost immediately, people around the world compared it to a mountain landscape illuminated by sunset. The resemblance is striking. Bright golden ridges appear to rise above shadowy valleys. Tall structures seem to stretch upward like cliffs weathered by millions of years of erosion. Yet every feature in the image is unimaginably larger than anything on Earth. Those apparent cliffs extend for several light years. Some of the structures would dwarf our entire solar system. Even the tallest mountain on Earth would become almost invisible against such scales. Mount Everest stands about 8.8 kilometers above sea level. The cosmic cliffs stretch across distances measured in trillions of kilometers. It's rather like comparing a grain of sand to a continent. Actually, even that comparison may be too generous. Scale in astronomy often becomes difficult because our everyday experiences provide no useful reference points. If you were somehow transported to this region, assuming you could survive the complete lack of breathable air, the intense radiation, and several other minor inconveniences, you wouldn't see towering rock walls. You would find yourself inside an enormous cloud of gas, a cloud so large that it spans distances almost impossible to imagine. And yet, despite its immense size, the gas is extraordinarily thin. Much thinner than the best vacuum chambers humans can build on Earth. This is one of the strange realities of space. Nebulae often look dense and solid in photographs. In reality, they are incredibly diffuse. If you gathered all the material inside a nebula and compressed it, you might end up with far less matter than most people expect. Space has a talent for looking crowded while remaining almost entirely empty. Still, these vast clouds perform one of the most important jobs in the universe. They create stars. Every star begins somewhere. The sun had a birthplace. Every point of light visible in the night sky had a beginning. Even the stars that disappeared billions of years ago once emerged from environments similar to this. Star formation is happening throughout our galaxy. But regions like the cosmic cliffs provide a particularly beautiful glimpse into the process. It's almost like nature accidentally left a construction site partially uncovered. For a brief moment we can peek inside and watch the universe at work, and what work it is. Stars are not manufactured in neat assembly lines. There are no cosmic engineers carrying clipboards, no giant instruction manuals floating through space. Instead, the process begins with gravity. Gravity is astonishingly patient. Unlike explosions or collisions, gravity doesn't need to hurry. It can spend millions of years accomplishing something. Given enough time, it slowly gathers gas together. Tiny differences in density become larger. Regions containing slightly more material attract even more material. Gradually, clouds begin to collapse inward. The process is slow, very slow. If humans measured their lives in millions of years, star formation might seem reasonably quick. From our perspective, however, it unfolds almost unimaginably gradually. Yet gravity never gets bored. It keeps pulling, keeps gathering, keeps building. Eventually, something remarkable begins to happen. The collapsing cloud grows hotter. As material falls inward, it gains energy. Temperatures rise, pressure increases. The growing object becomes denser and denser. For a very long time, it isn't technically a star. Astronomers call this stage a protostar, a star in preparation, a star under construction, a future sun waiting for its moment. Then, at last, conditions in the core become extreme enough for nuclear fusion to ignite. Hydrogen atoms begin combining into helium, energy floods outward, a new star is born. This process has happened countless times throughout cosmic history. It happened before Earth existed, before the sun existed, before complex life evolved, and somewhere inside the cosmic cliffs it is happening right now. Not metaphorically, not historically, right now. As you listen to this, new stars are forming. Some are hidden deep within dust clouds, others are just beginning to emerge. Many remain invisible to ordinary telescopes. One reason the James Webb Space Telescope created such excitement is its ability to see infrared light. Infrared wavelengths can penetrate dust much more effectively than visible light. It's a bit like switching from a flashlight to a special camera capable of seeing through fog. Suddenly, features that were hidden become visible, structures emerge, details appear. Entire populations of newborn stars reveal themselves. Before Webb arrived, astronomers already knew this region was active. After Webb arrived, they realized it was even more complex than expected. The image revealed jets, cavities, filaments, and countless young stars embedded within the cloud. Every one of those tiny points of light represents an object with its own story. Some may eventually host planets. Some may develop entire planetary systems. Some could survive for billions of years. Others may burn brightly and die comparatively young. Mass determines much of a star's destiny. The largest stars live surprisingly short lives. This often surprises people. We tend to associate bigger things with longer lifespans, bigger trees, bigger animals, bigger buildings. Stars follow different rules. Massive stars consume their fuel at astonishing rates. They are cosmic equivalents of engines permanently running at full throttle. A star many times more massive than the Sun may live only a few million years. Meanwhile, smaller stars can survive for trillions of years. Long after our Sun is gone, many red dwarf stars will continue shining. The universe has plenty of patience for small stars. As we look at the cosmic cliffs, we're witnessing the earliest stage of countless possible futures. Some of these newborn stars may eventually possess planets. Some planets may develop oceans. Some oceans may host chemistry complex enough to support life. And somewhere, billions of years from now, perhaps a curious species could gaze toward the sky and wonder where its own star came from. It's a strange thought. Every atom in your body was once part of a cosmic story like this. The hydrogen in your cells formed shortly after the Big Bang. The carbon in your body was forged inside ancient stars. The oxygen you breathe emerged from stellar furnaces long before Earth existed. You are, quite literally, connected to generations of stars that lived and died before the sun was born. The cosmic cliffs represent the next generation in that ongoing process, a place where the universe continues recycling material, continuing the cycle, continuing the story. And despite all the incredible technology involved, despite the telescopes, computers, detectors, and engineering marvels required to capture such images, there remains something wonderfully simple about what we're seeing. Gas, dust, gravity, time. The same ingredients that have shaped galaxies for billions of years. The same ingredients that helped create the sun. The same ingredients responsible for every star-filled night sky humanity has ever known. The deeper astronomers look, the more they discover that complexity often emerges from surprisingly simple beginnings. A cloud of gas becomes a star. A star creates heavier elements. Those elements form planets. On at least one planet, life appears. Eventually that life builds telescopes and looks back toward the clouds where stars are born. The universe has a habit of connecting beginnings and endings in unexpected ways. Several decades before the world heard the phrase cosmic cliffs, astronomers already knew that something extraordinary was happening deep within the Carina Nebula. Massive stars were being born there. Giant clouds of gas stretched across hundreds of light years. Powerful radiation blasted through space, shaping the surrounding material into strange and beautiful structures. Yet despite all our telescopes and technology, much of the region remained hidden. Imagine trying to study a forest while standing outside in dense fog. You can make out a few trees, you can see broad shapes, you know something interesting is there, but the details remain frustratingly out of reach. For many years, that's exactly how astronomers felt about parts of the Carina Nebula. The region itself had been known for centuries. European astronomers recorded observations of it during the 18th century, although indigenous peoples in the southern hemisphere had been observing and interpreting this section of the sky long before telescopes arrived. Located roughly 7,600 light-years away, the Carina Nebula is one of the largest stellar nurseries in our galaxy. If it were closer to Earth, it would dominate the night sky. People would likely point at it every evening. Children would grow up recognizing its shape. Poets would write about it. Weather forecasters would probably find a way to blame something on it. Fortunately for weather forecasters, it remains safely distant. Even so, astronomers have spent generations studying it. The reason is simple. Regions like the Carina Nebula allow us to witness stellar evolution in action. Most astronomical processes happen so slowly that humans never see significant changes during their lifetimes. Mountains erode slowly, galaxies evolve slowly. Stars live for millions or billions of years, but stellar nurseries contain enough activity that scientists can observe meaningful clues about how stars form and develop. By the late 20th century, increasingly powerful telescopes were revealing remarkable details. Radio observatories detected clouds of gas. Infrared instruments found young stars hidden behind curtains of dust. Space telescopes provided images far clearer than those possible from Earth's surface. Each generation of technology uncovered something new, and each discovery raised additional questions. This is one of science's favourite habits. Every answer tends to arrive carrying several fresh mysteries. The more astronomers learned about the Carina Nebula, the more they realised how dynamic the region actually was. massive stars already occupied portions of the nebula. These giant stars emitted enormous amounts of ultraviolet radiation. Their light wasn't merely illuminating the surrounding gas. It was actively changing it, heating it, compressing it, shaping it, sometimes even destroying it. A stellar nursery is not a peaceful place. When people hear the word nursery, they often imagine quiet rooms, soft lighting, and gentle lullabies. The universe has a rather different interpretation. A stellar nursery resembles an active construction zone combined with a demolition site. Stars are forming. Radiation is blasting outward. Shock waves move through clouds. Gas collapses under gravity. Other gas is pushed away by powerful stellar winds. Creation and destruction happen side by side. Long before the cosmic cliffs became famous, astronomers knew that this complicated interaction was occurring inside the Carina Nebula. What they lacked was a truly detailed view. Then came one of the most ambitious scientific instruments ever built, the James Webb Space Telescope. Getting Webb into space was not a simple undertaking. In fact, describing it as complicated might qualify as one of the gentlest understatements in engineering history. The telescope launched on December 25, 2021. While many people were opening holiday gifts, engineers and scientists around the world were nervously watching a rocket carry decades of work into space. The telescope itself represented the combined efforts of thousands of people: scientists, engineers, technicians, program managers, software developers, optics specialists. Entire careers had been invested in the project. The stakes were enormous. Unlike the Hubble Space Telescope, Webb was designed to operate far from Earth, about 1.5 million kilometers away. That's distant enough that astronauts cannot simply fly out and repair it if something goes wrong. Everything needed to work, thousands of components, hundreds of deployment steps, countless systems. One mistake could jeopardize the mission. Fortunately, things went remarkably well. Over the following months, Webb unfolded itself in space, its giant mirror segments aligned with astonishing precision, its instruments cooled to operating temperatures. Testing began. Then the first images started arriving. Scientists already expected impressive results. Webb was specifically designed to observe infrared light with unprecedented sensitivity. Infrared wavelengths can penetrate dust clouds that block visible light. Entire hidden regions of the universe would become accessible. Even so, expectations and reality turned out to be two different things. The telescope performed exceptionally well, better than many had dared hope. In July 2022, NASA released Webb's first collection of public images. Around the world, people stared at computer screens, televisions, and news articles. The images quickly became global news. Some revealed distant galaxies, others showed dying stars, still others displayed immense clouds of gas and dust. Among them was an image that immediately captured public imagination: the cosmic cliffs. Technically, the image showed a section of NGC 3324 located within the Carina Nebula, but almost nobody remembers that designation. Astronomical catalogue numbers are scientifically useful. They are not especially memorable. Cosmic cliffs, on the other hand, sounds like somewhere you might accidentally wander into during an interstellar hiking trip. The name stuck instantly, and for good reason. The image looked astonishingly familiar. Human beings are experts at recognizing landscapes. For hundreds of thousands of years, our ancestors relied on that skill. We instinctively identify horizons, valleys, ridges, and mountains. When people first saw Webb's image, many experienced the same reaction. It looked like a landscape, a vast golden mountain range rising above a dark plain. Towering peaks appeared illuminated by sunset. Shadows stretched across enormous valleys. Dust seemed to drift above ridgelines. The resemblance was almost uncanny. Of course, none of those features were actually mountains. There was no ground, no atmosphere, no sunlight setting behind distant peaks. Instead, The image captured the edge of a gigantic cloud sculpted by radiation from nearby stars. Yet the illusion remained powerful. Part of what made the image so compelling was its combination of familiarity and alienness. At first glance, it looked recognizable. A landscape, a mountain range, something earthly. Then your brain began processing the scale. Those structures weren't kilometers tall. They weren't even thousands of kilometers tall. Some extended across distances larger than entire planetary systems. The mountains existed within a cloud spanning light years. Suddenly, familiar became unimaginable. That's often where astronomy is most effective. It starts with something we understand, then slowly reveals how different reality truly is. Scientists examining Webb's data quickly noticed details that previous observations could not reveal clearly. Tiny points of light appeared throughout the cloud. Jets of material emerged from newborn stars. Dense knots of gas became visible. Complex structures hidden within the dust suddenly stood out. What looked like a single wall turned out to contain intricate layers and cavities. Some features resembled pillars, others resembled arches. Still others looked like gigantic fingers extending into space. Everywhere astronomers looked, they found evidence of ongoing star formation. This was not merely a beautiful picture, it was a scientific treasure. One reason the image generated so much excitement among researchers was the amount of information contained within it. Astronomy often depends on interpreting subtle clues, a slightly brighter region, a particular wavelength, a faint structure hidden in the background. Webb provided an extraordinary amount of detail. The telescope allowed scientists to study interactions between radiation and gas with unprecedented clarity. They could identify locations where star formation was actively occurring. They could trace flows of material. They could examine how nearby massive stars influenced their environment. Each observation added another piece to the puzzle. Meanwhile, the public response was equally enthusiastic. People who normally paid little attention to astronomy found themselves fascinated. The image spread across social media platforms. News organizations featured it prominently. Teachers incorporated it into classrooms. Art communities drew inspiration from it. Even individuals who rarely thought about space stopped to admire it. There's something remarkable about images that make millions of people pause simultaneously. For a brief moment, countless individuals around the world looked at the same patch of the universe. A cloud of gas 7,600 light-years away became part of everyday conversation. Not because of a discovery involving danger, not because of a crisis, not because of conflict, simply because it was beautiful. Science doesn't always receive that kind of attention. Often, important discoveries arrive quietly. Research papers are published, experts discuss them, life continues. The cosmic cliffs were different. The image possessed a rare combination of scientific value and visual appeal. You didn't need advanced knowledge of astrophysics to appreciate it. You could simply look at it and feel a sense of wonder. Then, if curiosity took hold, there was an entire universe of science waiting behind the image. That combination has always been powerful. Throughout history, beautiful observations have often inspired deeper investigation. People first admired the stars long before they understood them. They watched eclipses before understanding orbital mechanics. They observed planets before knowing what planets were. Wonder frequently arrives before explanation. The cosmic cliffs followed the same tradition. First came amazement, then questions. What are those structures? Why do they look like mountains? How large are they? What created them? Why are stars forming there? The more people learned, the more fascinating the region became. Ironically, one of the greatest achievements of the image was that it helped communicate an important scientific reality. The universe is not finished. Sometimes people imagine space as static, a collection of stars hanging motionless in darkness. But the universe is active. Stars form, stars die, clouds collapse, galaxies evolve, everything changes. The cosmic cliffs provided a snapshot of that ongoing activity, a moment frozen in time, a glimpse into processes that have operated for billions of years. Somewhere within those clouds, future stars were taking shape. Some might eventually possess planets. Some planets might orbit quietly for billions of years. Some may never host anything more complicated than rock and ice. Others could develop environments far stranger than anything we have imagined. The possibilities remain hidden in the future. For now, the image captures only the beginning, a birthplace, a construction site, a region where gravity, gas, radiation and time are working together to create the next generation of stars. A photograph can sometimes trick the brain in the most fascinating ways. When people first saw the cosmic cliffs image released by the James Webb Space Telescope, many assumed they were looking at something similar to a mountain range. The resemblance seemed obvious. There were towering ridges, there were shadowed valleys, there were bright edges illuminated by nearby stars. Some sections even looked like steep rock faces stretching toward a distant horizon. The impression was so strong that countless viewers described the image the same way. It looks like a landscape, and honestly it does. If someone showed you the picture without any explanation, you might reasonably assume it was a photograph of enormous mountains at sunset. Perhaps a desert canyon, maybe a rugged coastline seen from above. Yet none of those interpretations are correct. The cosmic cliffs are not mountains. They are not solid. They are not standing on any kind of ground. There is no horizon. There is no sky. There is no up or down. What we're actually seeing is a small section of a gigantic cloud floating freely through interstellar space. And that realization raises an important question. Where exactly are these cliffs? To answer that, we need to zoom out, far out, much farther than most of us are used to imagining. Let's begin with Earth. Our planet orbits the Sun at a comfortable distance of about 150 million kilometers. That sounds enormous, and by everyday standards it certainly is. If you attempted to drive that distance without stopping, assuming your car somehow survived the vacuum of space and several other technical challenges, the trip would take centuries. Yet in astronomical terms, Earth's orbit is tiny. The solar system itself extends far beyond the planets, beyond Neptune, beyond Pluto, beyond countless icy bodies drifting through darkness. Even then, the solar system occupies only a microscopic corner of a much larger structure, our galaxy, the Milky Way. The Milky Way contains somewhere between 100 billion and 400 billion stars. Astronomers are still refining that estimate because counting hundreds of billions of stars turns out to be surprisingly difficult. It's a little like trying to count grains of sand on a beach while standing in the middle of a sandstorm. The galaxy stretches roughly 100,000 light-years across. Our Sun sits far from the centre, orbiting quietly through one of the galaxy's spiral arms. From our perspective, the Milky Way feels immense, because it is. Light requires about 100,000 years to travel from one side to the other. Human civilization has existed for only a tiny fraction of that time. If the entire history of recorded civilization were converted into a road trip, crossing the galaxy would still take many thousands of times longer. Somewhere within this enormous galactic city lies the Carina Nebula. This is the larger region that contains the cosmic cliffs, and the Carina Nebula is anything but small. The nebula spans more than 300 light-years. To appreciate that scale, imagine replacing our Sun with the entire solar system. Not just the Sun, everything. Mercury, Venus, Earth, Mars, the gas giants, the icy objects beyond Neptune, the whole thing. Now imagine trying to compare that entire solar system to a structure hundreds of light-years across. The solar system would almost disappear. That's the challenge with stellar nurseries. They're so large that ordinary comparisons begin to break down. Located approximately 7,600 light-years from Earth, the Carina Nebula occupies part of the Carina Sagittarius arm of the Milky Way. This spiral arm is one of the major star-forming regions in our galaxy. In other words, if the Milky Way were a giant city, this would be one of its busiest construction districts. New stars are constantly appearing. Old stars influence their surroundings. Clouds of gas collapse. Radiation reshapes the environment. Everything is in motion. Everything is changing. The cosmic cliffs represent only a small section of that larger story. The specific region shown in the famous Webb image belongs to an area called NGC 3324. At first glance, that designation sounds more like a serial number than a destination, which, to be fair, is essentially what it is. Astronomers catalogue enormous numbers of objects, and eventually creativity gives way to efficiency. Still, behind that somewhat unromantic label lies one of the most active stellar nurseries ever observed. The cliffs themselves form the boundary between different environments. This is where things become especially interesting. What appears to be a giant wall is not really a wall. It only looks like one because of perspective. Imagine looking at a cloud from a particular angle. Certain portions might overlap. Some areas appear denser, others seem thinner. Your brain automatically interprets these visual clues and attempts to construct a three-dimensional picture. Sometimes it succeeds, sometimes it doesn't. The cosmic cliffs take advantage of this tendency. The image presents a two-dimensional view of an enormously complex three-dimensional structure. Gas and dust extend both toward us and away from us. Some regions overlap, others sit at completely different depths. The result creates the illusion of a giant cliff face. In reality, the structure resembles a tangled collection of ridges, cavities, pillars, and clouds, occupying a vast volume of space. It's less like a mountain range and more like a weather system frozen into place. Actually, even that comparison isn't quite accurate because weather systems on Earth exist within an atmosphere. The cosmic cliffs exist within the near vacuum of interstellar space. There is no wind in the conventional sense, no rain, no flowing rivers, no erosion caused by water, yet the landscape still changes. Something else is doing the sculpting. Radiation. Powerful radiation from nearby stars. This radiation acts almost like an invisible weather system. Massive stars located nearby emit enormous amounts of ultraviolet light. The energy pouring from these stars strikes surrounding gas clouds and begins reshaping them. Dense regions resist the assault. Less dense regions erode away. Over millions of years, the cloud develops intricate structures. Pillars emerge. Cavities form. Ridges survive. The resulting landscape looks remarkably similar to geological formations on Earth. The mechanisms are completely different. The appearance, surprisingly, is not. This resemblance reveals something interesting about nature. Very different processes can sometimes produce similar shapes. River erosion creates canyons, wind creates dunes, glaciers carve valleys, radiation sculpts nebulae. Different causes, similar patterns. The universe appears quite fond of reusing successful designs. As astronomers studied the region, they discovered that many of the visible structures are extraordinarily dense compared to their surroundings. Now, dense in astronomy often means something rather different than what people expect. A dense nebular cloud would still qualify as an exceptional vacuum by Earth standards. If you somehow scooped up a cubic meter of material from parts of the nebula, you would collect remarkably little actual matter. Space is mostly empty. Even regions we consider crowded remain astonishingly sparse. Nevertheless, tiny differences in density matter enormously over astronomical distances. Gravity notices these differences. Radiation notices them. Star formation depends on them. A slightly denser region attracts additional material. Additional material increases gravity. Gravity attracts more material. Over vast spans of time, tiny variations become significant. The universe often works this way. Small differences accumulate. Tiny advantages compound. Given enough time, modest beginnings become extraordinary outcomes. Many of the newborn stars hidden inside the cosmic cliffs began as subtle density fluctuations within a much larger cloud. Millions of years later, those tiny irregularities evolved into entire stellar systems. Some continue growing even now. Others have already emerged from their dusty birthplaces. And all of this is happening within a region that from Earth's perspective appears almost unimaginably distant. The distance itself creates another fascinating effect. When we observe the cosmic cliffs, we are not seeing them as they exist today. We're seeing them as they existed 7,600 years ago. This concept appears frequently in astronomy. Because light takes time to travel, every telescope functions as a kind of time machine, not the science fiction variety with flashing controls and complicated paradoxes, a much simpler version. Light leaves an object. Light travels. Eventually light arrives. The farther away something is, the further back in time we see. The cosmic cliffs therefore appear as they were thousands of years before the pyramids reached their final form, thousands of years before the Roman Empire, thousands of years before modern nations existed. For all we know, subtle changes have already occurred there, new stars may have formed, jets may have expanded. Cloud structures may have shifted, we simply haven't received the updated information yet. The newest version remains in transit. Astronomy constantly reminds us that distance and time are deeply connected. The farther we look, the older the universe becomes. Yet despite that enormous separation, observations of regions like the cosmic cliffs remain incredibly valuable. They allow us to study processes that once shaped our own cosmic neighbourhood. After all, the Sun almost certainly formed within a stellar nursery. Not necessarily one identical to the Carina Nebula, but something broadly similar. A giant molecular cloud. Regions collapsing under gravity. New stars emerging. Radiation influencing the environment. The same fundamental ingredients. The same physical laws. The same cosmic recipe. Somewhere within a cloud long vanished. Our sun began its life. The cloud disappeared billions of years ago. The evidence is largely gone. The birthplace has been erased by time. That's one reason astronomers treasure regions like the cosmic cliffs. They offer a chance to witness what our own origins may have resembled. Not exactly, but perhaps closely enough to provide important clues. Standing back and looking at the larger picture, the cosmic cliffs become something more than a beautiful image. They become a window into stellar birth, a place where gravity, radiation, gas and time interact on scales almost impossible to reproduce anywhere else. Far beyond Earth, beyond the familiar stars that fill our night sky, deep within the immense clouds of the Carina Nebula, a process is unfolding that has repeated itself for billions of years. It happens without sound, without urgency, without anyone directing it. No giant cosmic machine switches on. No invisible hand gives an order. Instead, something remarkably simple begins the entire process. Gravity. At first glance, gravity hardly seems dramatic enough for the job. Compared to exploding stars, black holes, or galaxies colliding, gravity can appear almost boring. It pulls things downward on Earth. It keeps planets orbiting stars. It causes you to drop your keys at the exact moment your hands are full. Yet gravity possesses one extraordinary advantage over nearly every other force in nature: patience. Gravity never gets tired. It never gets distracted. It never decides to take a day off. Given enough time, gravity can transform enormous clouds of gas into stars bright enough to illuminate entire solar systems. And inside the cosmic cliffs, that process is happening continuously. The famous image released by the James Webb Space Telescope shows towering walls of gas and dust stretching across light years of space. To human eyes, those structures appear solid and almost mountain-like. They seem permanent, sturdy, and unchanging. The reality is rather different. The cliffs are more like weather systems than mountains, enormous weather systems. Vast accumulations of gas and dust drifting through interstellar space. Yet hidden inside those clouds are regions where gravity has quietly begun its work. This hidden activity is one reason astronomers became so excited when Webb started observing the region. Visible light can only reveal part of the story. Dust blocks much of what lies behind it. It's a little like trying to understand a city while looking through dense fog. You might see rooftops, you might spot a few lights, but most of the activity remains concealed. Infrared observations change that. Infrared wavelengths can pass through dust much more effectively than visible light. Suddenly, objects that were hidden become visible. Entire populations of young stars emerge. Structures buried inside clouds reveal themselves. Features that once appeared dark and empty turn out to be crowded with activity. The cosmic cliffs are filled with such hidden activity. In fact, one could argue that the most important parts of the region are precisely the parts we cannot see with our own eyes. Because buried inside the dust are stellar nurseries, places where future stars are still growing, places where gravity is slowly turning clouds into suns. To understand how this happens, imagine an enormous cloud floating through space. This cloud is mostly hydrogen, the simplest and most abundant element in the universe. There is also helium, tiny amounts of heavier elements, microscopic dust grains, and an astonishing amount of empty space. Despite its immense size, the cloud is incredibly thin. If you could somehow stand inside one of these nebulae, you might not even realize it. The gas is so diffuse that it would appear almost invisible. Yet over distances measured in light years, even this sparse material adds up. The cloud contains enough mass to create thousands of stars, perhaps tens of thousands, perhaps more. For long periods, the cloud remains relatively stable. Gas drifts, temperatures remain low, nothing particularly dramatic happens, then something changes. Sometimes a nearby supernova sends a shockwave through the region. Sometimes neighbouring stars compress part of the cloud. Sometimes random fluctuations create slightly denser regions. The exact trigger varies. What matters is that certain areas become denser than their surroundings, and once that happens, gravity notices. Gravity always notices. A denser region possesses slightly stronger gravitational attraction. It pulls additional gas toward itself. As more material arrives, the region becomes even denser, which increases its gravity, which attracts even more material. A feedback loop begins, a very slow one, but a powerful one. Over time, the cloud starts collapsing. Not the entire cloud, only portions of it, like droplets forming inside a larger mist. Individual pockets begin shrinking under their own gravity. Astronomers call these regions dense cores. They are the earliest seeds of future stars. At this stage, nothing resembles a star yet. There is no fusion, no brilliant light, no stable sun shining in darkness. There is only gas slowly gathering together. The process unfolds over hundreds of thousands of years, then millions of years. Human beings rarely think in such timescales. Our lives are measured in decades. Civilizations are measured in centuries. Stars demand much greater patience. If you could somehow watch a stellar nursery in real time, you would see almost nothing happening. The changes occur too slowly. Entire generations would come and go before significant differences became visible. Fortunately, the universe provides many examples at different stages. Astronomers don't need to watch one star form from beginning to end. Instead, they can observe thousands of stars at various points in development. Together, these observations reveal a larger story. And that story tells us that gravity eventually wins. As the dense core contracts, something important begins to happen. The temperature rises. This surprises many people. Space is cold, very cold. The average temperature inside many nebulae is only a few dozen degrees above absolute zero. Yet collapsing gas naturally heats up. The reason is simple. As material falls inward, gravitational energy converts into heat. The shrinking cloud becomes warmer, and warmer, and warmer. The effect is similar to compressing air inside a bicycle pump. The compressed gas heats up. The same principle operates inside stellar nurseries, only on vastly larger scales. Eventually, a central object begins to emerge. Astronomers call this object a protostar. A protostar is not yet a true star. It has not started nuclear fusion. It shines primarily because of gravitational contraction. Material continues falling inward. The growing object continues heating up. The process resembles construction more than completion. The star is still being assembled. Inside the cosmic cliffs, numerous protostars occupy precisely this stage. Many remain hidden within dense cocoons of gas and dust. Webb's infrared instruments revealed some of them for the first time. Tiny red points scattered throughout the cloud, each one representing a future sun. Each one a reminder that star formation is ongoing. One of the remarkable things about stellar nurseries is that no two stars form exactly the same way. The overall process remains consistent. Gravity gathers gas, the cloud contracts, a protostar emerges, fusion eventually ignites. Yet the details vary enormously. Some stars form alone, others form in pairs, many form in groups. Entire clusters can emerge from a single giant cloud. In fact, astronomers believe our own Sun likely formed as part of a larger stellar family. Billions of years ago, the Sun probably had hundreds or even thousands of sibling stars. Over time, those siblings drifted apart. The original cluster dispersed. Today, those stars are scattered throughout the Milky Way. Finding them is extraordinarily difficult. It's rather like trying to identify people who attended the same kindergarten 4.5 billion years ago. Nevertheless, the evidence suggests that stars rarely form in complete isolation. The cosmic cliffs demonstrate this beautifully. Instead of a single star emerging from a cloud, entire populations are forming together. Young stars occupy the region at different stages of development. Some are only beginning their collapse. Others have already ignited fusion. Still others are actively reshaping the surrounding environment. The nursery contains multiple generations living side by side. Older stars influence younger stars. Radiation alters nearby clouds. New regions become compressed. Fresh waves of star formation begin. The entire environment functions as a connected system. And this is where the story becomes even more interesting, because gravity is not working alone. Massive stars already present within the Carina Nebula exert enormous influence over the region. Their radiation floods the surrounding space. Their stellar winds push material outward. Their energy sculpts the clouds we see in Webb's image. In some places, this activity disrupts star formation. Gas gets blown away. Potential future stars lose the material they need. In other places, however, the opposite occurs. Compression caused by radiation and stellar winds can trigger collapse. New dense regions form. Gravity takes over. Additional stars begin developing. The result is a complex balance between creation and destruction. Massive stars both help and hinder the formation of future generations. The universe often works this way. Processes rarely have only one consequence. Actions create multiple effects, some constructive, some destructive, often both simultaneously. Standing at the scale of a stellar nursery, this becomes especially apparent. A newborn massive star might eventually destroy portions of the cloud that created it, yet that same destruction can trigger additional star formation elsewhere. The cloud evolves, changes shape, future changes. The cycle continues. Inside some of the densest regions, young protostars are surrounded by rotating disks of material. These disks are particularly important. They represent the raw ingredients from which planetary systems can emerge. Gas spirals inward toward the growing star. Dust particles collide. Small grains become larger grains. Larger grains become pebbles. Pebbles become rocks. Over vast periods, entire planets may eventually develop. This means that when astronomers observe stellar nurseries, they are not merely watching stars form. They are potentially witnessing the earlier stages of future worlds. Some of those worlds may remain barren. Some may become gas giants. Some may develop oceans, some may possess conditions suitable for life. At this stage, nobody knows. The future remains hidden, yet the ingredients are already present. The process has already begun. Every planet in our solar system traces its origins back to a similar environment. Earth began inside a protoplanetary disk. So did Mars, so did Jupiter. The atoms themselves are much older. Many originated inside ancient stars that lived and died before the Sun existed. Their remnants mixed into giant molecular clouds. Those clouds eventually produced new generations of stars and planets, and eventually life. The cosmic cliffs provide a glimpse of that same cycle repeating itself, not as history, not as theory, as an ongoing reality. At this very moment, somewhere within those clouds, future solar systems are taking shape. Future planets are beginning their long journey toward existence. Future skies are being prepared. The scale of the process can feel overwhelming. Distances measured in light years, timescales measured in millions of years, clouds larger than entire planetary systems. Yet beneath all that complexity lies a surprisingly simple principle. Gravity gathers matter. Given enough matter and enough time, stars appear. The universe has been following this recipe for most of its history, and it continues following it today, long after humanity arrived, long before humanity existed, long after humanity is gone. Gravity will continue its quiet work. Clouds will continue collapsing, stars will continue forming. The cosmic cliffs are simply one location where we happen to witness the process particularly clearly. Long before a star shines across the darkness of space, long before planets orbit around it, and long before anyone could ever look up from a world beneath its light, the story begins in near complete darkness. Not the darkness we experience on Earth, not a moonless night, not a dark room, something far deeper. The darkness found inside dense clouds of gas and dust, where visible light struggles to penetrate. This is where every star begins. The stars visible above your head tonight all started this way. The sun began this way. Every bright point scattered across the Milky Way followed some version of the same journey. And inside the cosmic cliffs, countless future stars are currently taking their first steps along that path. What's remarkable is that stars are born from some of the coldest environments in the universe. Many people imagine stars beginning in fire. That seems reasonable. After all, stars eventually become enormous balls of hot plasma. The sun's surface reaches temperatures of roughly 5,500 degrees Celsius. Its core exceeds 15 million degrees Celsius. Heat defines what a star becomes. Yet the process begins with cold. Extremely cold. Parts of stellar nurseries can reach temperatures around minus 260 degrees Celsius, only a few degrees above absolute zero. At such temperatures, atoms move sluggishly. Energy levels remain low. The cloud appears calm, still, quiet. But appearances can be deceptive, because gravity is already at work. As we explored earlier, tiny differences in density begin attracting surrounding material. A slightly denser region gathers additional gas. Its gravity strengthens. More gas arrives. The process continues, slowly, patiently, relentlessly. Over hundreds of thousands of years, the cloud begins collapsing inward. At first, the collapse occurs almost invisibly. No brilliant flashes announce the event. No giant explosions signal the beginning. The cloud simply grows denser. Material gradually concentrates toward the center. The region shrinks. The density rises. Gravity tightens its grip. If we could somehow watch the process unfold at accelerated speed, we would see enormous streams of gas flowing inward from every direction. Not neatly, not symmetrically. Real stellar nurseries are messy places. Turbulence twists through the clouds. Magnetic fields influence motion. Nearby stars affect conditions. The collapse resembles a complex weather system more than a perfectly organized construction project. Nevertheless, The overall trend remains clear. Matter moves inward. The central region grows. Eventually, enough material accumulates that something new begins to emerge. A protostar. Astronomers use this term to describe an object that is on its way to becoming a true star, but hasn't reached the finish line yet. The distinction matters. A protostar may look impressive. It may already possess significant mass. It may even emit considerable energy, yet it remains incomplete. Nuclear fusion has not fully begun. The object is still under construction. Inside the cosmic cliffs, Webb has revealed numerous protostars hidden within dense clouds. Many remain wrapped inside cocoons of gas and dust. From the outside, they are difficult to observe. Visible light struggles to escape. Infrared observations, however, can reveal their presence. Suddenly, regions that once appeared dark become crowded with activity. Tiny points of light emerge. Young stellar objects reveal themselves. Entire populations of developing stars appear where astronomers previously saw mostly darkness. One of the fascinating things about protostars is that they don't simply sit there while material falls inward. The process creates enormous amounts of activity. As gas spirals toward the centre, conservation of angular momentum comes into play. This principle sounds complicated, but you've experienced it before. Imagine an ice skater spinning with arms extended. When the skater pulls their arms inward, they spin faster. The same basic idea applies to collapsing clouds. As material falls inward, rotation increases. Instead of plunging directly into the centre, gas often forms a rotating disk around the growing protostar. These disks are among the most important structures in astronomy. Not because they create stars, because they create planets. Every major planet in our solar system originated within such a disk. Earth formed there, Mars formed there, Jupiter formed there. The raw ingredients of future worlds first gathered within a rotating cloud surrounding a newborn sun. The same process appears throughout the galaxy. Everywhere astronomers observe young stars, they frequently discover disks. Some are large, some are small, some survive for millions of years, others disappear more quickly. Together they represent the natural consequence of stellar birth. A new star forms, a disk appears, potential planetary systems begin developing. Looking at the cosmic cliffs, we are not merely observing future stars, we are potentially observing future planetary systems, future Earths, future Jupiters, future worlds unlike anything humanity has yet imagined, all hidden within clouds of dust. As the protostar continues growing, temperatures rise steadily. The reason is straightforward. Material falling inward converts gravitational energy into heat. The more matter accumulates, the stronger gravity becomes. The stronger gravity becomes, the more energy gets released during collapse. The centre grows hotter, and hotter, and hotter. Millions of degrees eventually become possible. At this stage, the protostar resembles a giant pressure cooker. Gravity pushes inward, heat pushes outward, the battle intensifies. For a while, gravity remains stronger. The collapse continues. Additional material arrives. The object grows larger. Then the critical moment approaches. Deep within the core, temperatures become extreme enough for hydrogen nuclei to begin overcoming their mutual electrical repulsion. Ordinarily positively charged hydrogen nuclei repel one another. They're not particularly interested in merging, yet under tremendous pressure and temperature, collisions become energetic enough for fusion to occur. Two nuclei come together. Energy is released. More fusion follows. The process accelerates. Suddenly, a new source of power appears. Not gravitational energy, nuclear energy. This changes everything. Fusion produces an extraordinary amount of energy. The process powering the sun converts only a tiny fraction of mass into energy, yet the resulting output is enormous. Every second, the sun releases more energy than human civilization could use over vast spans of time, and it has been doing so for billions of years. The moment sustained fusion begins, a true star is born. Astronomers sometimes refer to this stage as reaching the main sequence. The star has arrived. The long construction process is complete. A stable balance emerges. Gravity continues pulling inward. Fusion pushes outward. Neither side wins. Instead, equilibrium develops. The star stabilizes. This balance may persist for millions, billions, or even trillions of years, depending on the star's mass. Mass turns out to be the most important factor in determining a star's future. The amount of material gathered during formation influences nearly everything that follows. A small star lives differently than a massive star. It shines differently. It evolves differently. It dies differently. The universe creates tremendous variety simply by changing the amount of material available during formation. Some stars acquire only a fraction of the Sun's mass. Others become dozens or even hundreds of times more massive. The differences produce dramatically different outcomes. A small red dwarf burns fuel slowly and efficiently. Such stars may survive for trillions of years. Many existing red dwarfs will outlive every larger star currently shining. Massive stars follow another path entirely. They burn fuel at astonishing rates. Their luminosity becomes extraordinary. Their lifespans become short. A star dozens of times more massive than the Sun might live only a few million years. That sounds like a long time to us. Astronomically speaking, it's remarkably brief. Some of the giant stars influencing the cosmic cliffs today are already living on borrowed time. They formed relatively recently, yet they may disappear long before smaller neighbouring stars have reached middle age. The irony is striking. The biggest stars often have the shortest lives. It's a bit like building the world's most powerful engine and discovering it consumes fuel at an alarming rate. Brightness comes with a price. Meanwhile, young stars rarely experience a peaceful childhood. Popular illustrations sometimes depict newly formed stars as neat, glowing spheres quietly shining in darkness. Reality tends to be more chaotic. Many young stars produce powerful jets. Material gets launched from their poles at tremendous speeds. These jets can stretch for light years. They slam into surrounding gas. Shock waves form. Complex structures emerge. Astronomers observe such phenomena throughout stellar nurseries. The cosmic cliffs contain numerous examples. Webb's observations revealed jets, outflows, and disturbances associated with newborn stars. These features provide valuable clues about ongoing formation processes. Each jet acts like a signpost. Something is happening here. A young star is growing. Material is moving. Energy is being released. The nursery remains active. The region is alive with change. Another surprising aspect of stellar birth involves efficiency. One might assume giant clouds of gas simply turn themselves into stars. The truth is more complicated. Most of the available material never becomes part of a star. Radiation disperses gas. Stellar winds push material away. Turbulence redistributes matter. Only a fraction of the original cloud ends up inside stars. Nature is surprisingly wasteful during star formation. Or perhaps efficient in a different sense. The leftover material helps shape future generations. Clouds evolve. New regions collapse. Fresh stars emerge. The cycle continues. Nothing remains static. Inside the cosmic cliffs, this cycle is unfolding on a grand scale. Dense pockets are collapsing. Protostars are growing. Fusion is beginning. Young stars are influencing their surroundings. Future generations are already being prepared. And all of it is happening inside structures that, from Earth, resemble enormous mountains frozen in space. The deeper astronomers investigate these nurseries, the clearer it becomes that star formation is not a simple sequence of events, but a dynamic interaction between gravity, radiation, gas, magnetic fields, and time itself. What appears in the famous image of the cosmic cliffs looks surprisingly permanent. The towering walls seem solid. The ridges appear ancient. The pillars look as though they have stood unchanged for ages. If you had no context, you might assume you were looking at geological formations that had existed for millions of years without significant alteration. On Earth, mountains often create that impression. A cliff face appears immovable. A canyon seems eternal. A rocky ridge can feel older than imagination itself. Yet the structures inside the cosmic cliffs tell a very different story. They are not static. They are not permanent. They are actively changing, even now, at this very moment. The giant walls, pillars and caverns revealed by the James Webb Space Telescope are being sculpted by forces that never stop operating. Unlike mountains on Earth, which are shaped primarily by wind, water, ice and tectonic activity, the cosmic cliffs are being carved by something invisible: radiation, light itself. This may sound strange at first. Most of us think of light as something gentle. It illuminates rooms, it brightens landscapes, it helps us read books. We don't usually think of light as a tool capable of reshaping enormous regions of space, but inside stellar nurseries, radiation becomes one of the most powerful sculptors in the universe. To understand how this works, imagine the environment surrounding the cosmic cliffs. Nearby, scattered throughout the Carina Nebula, are some of the most massive stars in our galaxy. These stars are not ordinary. Many possess dozens of times the Sun's mass. Some shine hundreds of thousands, or even millions of times more brightly than the Sun. Their energy output is almost difficult to comprehend. Every second they release staggering amounts of radiation into the surrounding space. Not merely visible light, not merely warmth, but intense ultraviolet radiation. This ultraviolet light carries enormous energy, enough energy to dramatically alter nearby gas clouds, and that is exactly what it does. When ultraviolet radiation strikes a cloud of hydrogen gas, something important happens. The radiation strips electrons away from hydrogen atoms. Astronomers call this process ionization. The resulting gas becomes electrically charged. It also becomes significantly hotter. Temperatures can rise to thousands of degrees. Suddenly, a quiet cloud finds itself under assault from a constant flood of energetic radiation. The effects accumulate over time. Gas begins expanding. Pressure increases. Material gets pushed away. The cloud starts changing shape. Imagine leaving a block of ice under a heat lamp. The lamp doesn't physically touch the ice, yet the ice gradually changes. Material disappears. Edges soften. The shape evolves. Radiation acts somewhat similarly inside stellar nurseries, although the physics involved is considerably more complex. The giant stars surrounding the cosmic cliffs function like immense cosmic heat lamps. For millions of years they have been bombarding nearby clouds with energy. The result is the spectacular landscape we see today. What's especially fascinating is that radiation does not affect every part of the cloud equally. Some regions are denser than others, some contain more material, some possess stronger gravitational binding. These denser regions resist erosion more effectively. The less dense regions disappear first. This uneven process gradually creates structure. Imagine a rainstorm falling on a landscape containing both hard rock and soft soil. The softer material erodes faster. The harder material survives longer. Over time, distinctive formations emerge. The cosmic cliffs follow a surprisingly similar principle. Dense regions survive. Less dense regions vanish. The surviving material eventually appears as ridges, pillars, and walls. Nature is essentially performing selective erosion. Only the tools are different. Instead of rain and rivers, the sculpting agents are photons and ionized gas. Instead of thousands of years, the process unfolds across millions of years. The resulting structures can become enormous. Some of the pillars visible inside stellar nurseries stretch across distances larger than entire planetary systems. Others extend for multiple light years. Their scale is almost impossible to appreciate fully. Even the tallest mountain ranges on Earth become tiny by comparison. One of the reasons these formations look so dramatic is that our brains instinctively interpret them as landscapes. We recognize vertical structures, we recognize shadows, we recognize ridges and valleys. The image feels familiar. Yet if we could somehow travel there, the experience would be utterly alien. There would be no ground beneath our feet, no atmosphere overhead, no horizon, only immense clouds suspended within space. The apparent cliffs would surround us in 3 dimensions. Some sections would extend toward us, others would stretch behind us. The famous image compresses this complexity into a 2-dimensional view. The result is beautiful. But it also hides just how intricate the region really is. Astronomers studying the area have discovered that many of the visible structures are actually part of a larger network. Pillars connect to ridges. Ridges connect to dense clouds. Clouds connect to enormous reservoirs of gas extending far beyond the image itself. Everything is linked. Nothing exists in isolation. The nursery functions as a single evolving environment. And evolution is exactly what is happening. The landscape is not frozen. It is actively changing. The radiation never stops. Every second, nearby stars continue blasting the cloud with energy. Material continues evaporating. Cavities continue expanding. Pillars continue shrinking. The structures visible today will not exist forever. Given enough time, many will disappear entirely. This idea often surprises people. The cosmic cliffs look ancient. They look permanent. Yet they are temporary features. Beautiful temporary features. The same radiation that helped create them will eventually destroy them. In astronomy, creation and destruction frequently happen together. The processes that build something often contain the seeds of its eventual disappearance. A star forms. The star begins radiating energy. That energy reshapes the cloud. The cloud changes. Some regions vanish. Others survive. New stars form. The cycle continues. Nothing remains fixed. One particularly interesting consequence of radiation-driven erosion is the creation of cavities. Throughout the Carina Nebula, astronomers observe enormous bubbles and hollow regions. Some stretch for dozens of light years. At first glance, these cavities appear empty. In reality, they are evidence of tremendous activity. Massive stars produce powerful stellar winds. These winds consist of streams of charged particles moving at extraordinary speeds. Combined with ultraviolet radiation, they push surrounding material outward. Over time, giant cavities emerge. The process resembles blowing air into a balloon. The surrounding gas gets displaced. A hollow region forms, except these cosmic bubbles are vastly larger than anything encountered on Earth. Some could easily contain many solar systems. Others could contain entire star clusters. The scale remains almost absurd. Yet these cavities play a crucial role in shaping stellar nurseries. As they expand, they compress nearby clouds. Compression increases density. Density strengthens gravity. Gravity encourages collapse. New stars begin forming. Ironically, the stars already present in the region help trigger the birth of future stars. This phenomenon is sometimes called triggered star formation. It represents one of the most fascinating feedback loops in astronomy. Massive stars influence their environment. The environment responds. New stars emerge. Those stars eventually influence the environment in turn. The cycle repeats. The cosmic cliffs offer a particularly striking example of this process. The apparent walls mark a boundary between different conditions. On one side lies relatively dense material. On the other side lies gas already altered by radiation. The interaction zone creates spectacular structures. Every ridge tells part of the story. Every pillar records a history of erosion and resistance. Every cavity reveals where radiation has gained the upper hand. Some of the most intriguing formations appear near regions where newborn stars are still hidden. These dense pockets have survived because they contain enough material to resist complete erosion. In many cases, they are actively forming stars. The surviving cloud essentially acts like a protective cocoon. Inside, gravity continues working. Protostars continue growing. Future suns continue developing. Outside, radiation relentlessly attacks the cloud. The contrast creates dramatic landscapes, but it also creates opportunity. Without radiation, the cloud might remain relatively uniform. Without dense pockets, stars might never form. The interaction between these opposing influences helps drive the evolution of the entire region. Astronomers often describe stellar nurseries as battlegrounds between competing forces. Gravity pulls inward, radiation pushes outward, gas cools, stars heat, clouds collapse, clouds disperse. No single force dominates forever. Instead, the landscape emerges from continuous interaction. The cosmic cliffs showcase that interaction beautifully. The structures we admire are essentially snapshots of an ongoing contest, a contest unfolding over millions of years, a contest that determines where future stars will appear, a contest that shapes the architecture of entire regions within the galaxy. What's particularly remarkable is that these processes are not unique to the Carina Nebula. Similar structures appear throughout the Milky Way. Astronomers observe pillars inside the Eagle Nebula. They observe cavities in countless stellar nurseries. They observe radiation sculpting clouds across the galaxy. The same physical laws operate everywhere. The cosmic cliffs simply provide one of the clearest examples ever observed. Thanks to Webb's extraordinary capabilities, we can see details that previous generations of astronomers could only imagine. Tiny structures become visible. Hidden stars emerge. Complex patterns reveal themselves. The image transforms from a beautiful photograph into a scientific laboratory. Every feature contains information. Every shadow tells a story. Every ridge reflects millions of years of interaction between matter and energy. Thousands of years before the first human looked up and wondered what stars were, long before telescopes existed, and billions of years before the James Webb Space Telescope revealed the cosmic cliffs in extraordinary detail, a group of stellar giants began reshaping part of the Carina Nebula. They are still doing it today. Everything we've discussed so far, the towering walls, the ridges, the pillars, the caverns, the glowing edges of the cosmic cliffs, ultimately traces back to these stars. Without them, the landscape would look completely different. Without them, many of the structures that make the cosmic cliffs so visually striking would never have formed. Without them, some of the stars currently growing inside the nebula might never have been born at all. And yet these giants are not builders in the conventional sense. They don't construct the cliffs. They don't carefully assemble the landscape. Instead, they reshape it through sheer power by simply existing. To appreciate what these stars are doing, it helps to begin with our own sun. The sun feels enormous from our perspective. It contains about 99.8% of all the mass in the solar system. More than 1 million Earths could fit inside it. Its gravity controls the motions of planets, moons, asteroids and comets. Its light powers Earth's climate. Its energy supports nearly every ecosystem on our planet. For human beings, the sun seems unimaginably powerful, and it is. Yet within the Carina Nebula, the sun would barely attract attention. This is not meant as an insult. The sun is a perfectly respectable star, stable, reliable, long-lived, an excellent choice for supporting life. But compared to the giants inhabiting stellar nurseries like Carina, it is relatively modest. Some stars inside the nebula possess 20, 30, 50, or even more times the sun's mass. Others shine hundreds of thousands of times brighter. A few release more energy in a single second than humanity has consumed throughout its entire history. The scale becomes difficult to grasp. Imagine replacing a household flashlight with a lighthouse, then replacing the lighthouse with a stadium floodlight, then replacing the stadium floodlight with something visible from another continent. The comparison still falls short. Massive stars operate on levels almost disconnected from everyday experience. Astronomers classify many of these objects as O-type stars. These are among the hottest, brightest and most massive stars known. They represent a tiny fraction of all stars in the Milky Way. Most stars are much smaller. Most stars are cooler. Most stars are less dramatic. O-type stars are the celebrities of stellar nurseries. Bright, powerful, rare, and impossible to ignore. One reason they exert such influence is that luminosity does not increase in a simple way as mass increases. A star twice as massive as another does not merely become twice as bright. The relationship is far more extreme. Massive stars release vastly greater amounts of energy. Their ultraviolet radiation floods surrounding space. Their stellar winds blast through nearby clouds. Their presence changes everything around them. This is exactly what happened inside the Carina Nebula. The giant stars formed first, or at least earlier than many of the stars currently developing inside the cosmic cliffs. Once they ignited, they began altering the environment immediately. Energy streamed outward. Radiation spread through the nebula. Shock fronts developed. Clouds compressed. Other clouds eroded. The landscape entered a new phase of evolution. It's helpful to think of these stars as giant engines operating continuously. Unlike engines on Earth, however, they never switch off. Every second, enormous quantities of energy leave their surfaces. Every second, photons race outward into surrounding space. Every second, particles stream away in stellar winds. The process continues day and night, year after year, million year after million year. The stars never pause, and because they never pause, their influence accumulates. A single second changes little. 1,000 years changes more. 1,000,000 years changes everything. One of the most important effects involves ultraviolet radiation. Earlier we discussed how ultraviolet light can ionize gas. This process strips electrons away from atoms. The gas becomes energized. Temperatures rise. Pressure increases, cloud structures begin changing. Now imagine this process occurring continuously for millions of years. That's what the giant stars inside Carina have been doing. The cumulative effects become enormous. Regions of the nebula begin glowing. Dense clouds develop sharp edges. Vast cavities emerge. Entire sections of the cloud disappear. The famous cliffs visible in Webb's image are partly the result of this prolonged interaction. The stars are sculpting the landscape through radiation, not intentionally, not consciously, simply as a consequence of being extraordinarily luminous. What's especially interesting is that these giant stars can influence regions located many light years away. Distance matters less when your energy output becomes large enough. The radiation spreads outward through enormous volumes of space. Clouds far from the star still feel the effects. In some areas, gas gets pushed aside. In others, it becomes compressed. The result is a nebula constantly changing shape, a nebula being remodeled by its brightest inhabitants. And radiation is only part of the story. The stellar winds matter too. The phrase stellar wind sounds surprisingly gentle, almost refreshing. Perhaps something you'd enjoy during a warm afternoon. The reality is considerably less relaxing. A stellar wind consists of charged particles racing away from a star at tremendous speeds. Some travel hundreds or even thousands of kilometers every second. Over time, these winds carry substantial amounts of energy into the surrounding environment. Imagine standing in front of an industrial pressure washer. Now imagine scaling that process up to astronomical proportions. The comparison remains inadequate, but it points in the right direction. Stellar winds push against surrounding gas. They carve cavities. They compress clouds. They contribute to the formation of bubbles spanning dozens of light years. Many of the hollow regions observed throughout the Carina Nebula owe their existence to these winds. The stars are effectively blowing giant holes into their surroundings. The process unfolds slowly by human standards, yet over millions of years the results become spectacular. Some cavities become so large that they fundamentally alter the structure of the entire nebula. Others merge with neighbouring cavities. Complex networks emerge. The environment evolves continuously. And this evolution creates a fascinating paradox. The giant stars simultaneously destroy and create opportunities for new stars. At first glance, destruction seems easier to understand. Radiation erodes clouds, winds disperse gas, material gets blown away, potential star-forming regions disappear. Simple enough. Yet the same processes can also trigger star formation. When radiation and stellar winds compress a cloud, density increases. Higher density strengthens gravity. Stronger gravity encourages collapse. Collapse produces protostars. Protostars become stars. The giant stars therefore help create the next generation, not everywhere, not all the time, but often enough to matter. Astronomers see evidence of this throughout the galaxy. One generation influences the next. Older stars reshape clouds. New stars emerge from those reshaped clouds. The cycle continues. Inside the cosmic cliffs, this interaction is happening right now. Some regions are being eroded. Others are being compressed. Some future stars may never form because material is being stripped away. Other future stars may form specifically because the compression triggered collapse. The landscape records both outcomes simultaneously. This is one reason stellar nurseries fascinate astronomers. The environment is dynamic. Nothing remains fixed. Every force influences every other force. Every change produces additional changes. The system behaves less like a static photograph and more like a living ecosystem. Different processes compete. Different outcomes emerge. The nebula evolves. Another remarkable feature of giant stars is their temperature. The Sun's surface temperature sits around 5,500 degrees Celsius, hot enough to vaporize any earthly material, hot enough to dominate an entire planetary system. Yet many O-type stars possess surface temperatures exceeding 30,000 degrees Celsius. Some approach 50,000 degrees. At those temperatures, enormous quantities of ultraviolet radiation become inevitable. The stars glow with incredible intensity. Their light affects everything nearby, and because they are so bright, they become visible across immense distances. Astronomers can identify giant stars in other galaxies, not because the stars are close, but because they are luminous enough to stand out even from millions of light years away. Brightness becomes a kind of cosmic signature. The stars announce their presence across the universe. Yet despite all their power, giant stars face a significant problem. They consume fuel at astonishing rates. Earlier we touched on this idea, but it deserves deeper exploration. People often assume larger objects last longer. Larger buildings, larger reservoirs, larger batteries. Massive stars refuse to follow this logic. They burn through fuel with extraordinary intensity. The same processes that make them bright also shorten their lives. A star 20 or 30 times more massive than the Sun may survive only a few million years. Astronomically speaking, that's barely an introduction. The Sun, by comparison, enjoys a lifespan measured in billions of years. Massive stars live fast, very fast, and their endings become just as dramatic as their lives. Eventually, many explode as supernovae. These explosions release staggering amounts of energy. For a brief period, a single star can outshine an entire galaxy. The blast waves race outward through space. Nearby clouds get compressed. Heavy elements scatter throughout the region. New opportunities for star formation emerge. The cycle begins again. In fact, some astronomers suspect that previous generations of giant stars helped shape the environment that eventually produced the stars we see inside Carina today. The nebula contains evidence of multiple generations, older stars, younger stars, stars still forming. The region resembles a cosmic family tree extending across millions of years. Each generation influences the next. Each generation inherits material from those that came before. The process has been operating throughout much of galactic history. The atoms inside your body participate in that story. The carbon in your cells originated inside ancient stars. The oxygen you breathe formed through stellar processes. The calcium in your bones traces its origins to long-dead stars. The giant stars shaping the cosmic cliffs today are manufacturing elements that future generations may someday inherit. Perhaps future planets, perhaps future life, perhaps future civilizations. The chain of cause and effect stretches across billions of years, and all of it begins with stars. Looking again at the cosmic cliffs, it's easy to focus on the visible structures, the ridges, the pillars, the glowing edges. Yet behind every feature stands the influence of these stellar giants. They provide the energy. They drive the erosion. They create the cavities. They trigger new collapses. The landscape is effectively a record of their activity, a visible history written into clouds of gas and dust. Few things in astronomy seem more harmless than light. It brightens a room. It illuminates a landscape. It helps us see distant objects. Most of our everyday experiences teach us to think of light as passive. Light reveals things. Light allows observation. Light helps us understand the world around us. But deep inside the Carina Nebula, light is not merely revealing the landscape, it is creating it. The giant walls, towering ridges, narrow pillars, and dramatic caverns visible throughout the cosmic cliffs exist largely because light has been actively reshaping the environment for millions of years. In this region, light is not a spectator. It is an architect, a sculptor, a force capable of altering structures that stretch across light years of space. And perhaps the most remarkable part is that it accomplishes this without touching anything in the way we normally imagine physical forces interacting. No giant cosmic hand carves the cliffs. No invisible machinery cuts through the clouds. The sculpting happens because energy flows continuously from massive stars into their surroundings. To understand how extraordinary this is, let's begin with a simple thought experiment. Imagine standing outdoors on a sunny day. You can feel sunlight warming your skin. The sunlight carries energy. Enough energy to warm rocks, heat roads, and power entire ecosystems. Plants depend on it. Weather systems depend on it. Life on Earth depends on it. Yet compared to the radiation pouring from the giant stars of the Carina Nebula, sunlight is surprisingly gentle. The sun emits enormous amounts of energy, but many of the stars influencing the cosmic cliffs release vastly more. Some shine hundreds of thousands of times brighter. Others approach 1,000,000 times the sun's luminosity. Every second, staggering amounts of energy flood outward from their surfaces. That energy travels through space until it encounters something, and inside the nebula there is plenty to encounter. Clouds of hydrogen, clouds of helium, dust grains, dense pockets of gas, filaments stretching across enormous distances. The interaction between light and these clouds gradually transforms the landscape. At first, the process seems almost insignificant. A photon strikes an atom. An electron gets removed. A tiny amount of energy transfers into the gas. One event, then another, then trillions upon trillions more. The power comes not from any individual interaction, but from the sheer number occurring continuously. The stars never stop shining. The radiation never stops arriving. The cloud never stops responding. Over time, small changes become large ones. This pattern appears repeatedly throughout nature. A single raindrop accomplishes little. Millions of raindrops carve valleys. A single ocean wave changes almost nothing. Millions of waves reshape coastlines. Likewise, a single photon barely affects a nebula. Billions upon billions of photons arriving for millions of years can transform entire regions of space. Inside the cosmic cliffs, this transformation is visible everywhere. The bright edges seen in Webb's famous image represent areas where intense radiation is striking dense clouds. These boundaries mark active regions of interaction. They are not static lines, they are moving fronts, locations where the landscape is currently being reshaped. In some places the cloud resists, in others it yields. The result is a constantly evolving structure. Astronomers often compare the process to erosion on Earth. The comparison isn't perfect. The underlying physics differ dramatically, yet both processes share an important characteristic. They remove material unevenly. And uneven removal creates structure. Imagine a landscape containing both hard rock and soft rock. Wind and water gradually wear away the softer material. The harder sections survive longer. Over time, pillars emerge, cliffs appear, valleys deepen. Nature turns differences in resistance into visible features. The cosmic cliffs follow a surprisingly similar principle. Some regions of the cloud are denser, some contain more material, some possess stronger gravitational binding. These regions resist radiation more effectively. Less dense material disappears first. Dense regions remain. Eventually what survives becomes visible as ridges, towers and walls. The landscape literally emerges through selective survival. It's a process operating on scales that are difficult to imagine. On Earth, a dramatic canyon might extend for a few hundred kilometers. Inside the Carina Nebula, individual structures can stretch for multiple light years. A single light year equals nearly 10 trillion kilometers. Even the largest geological formations on Earth seem tiny by comparison. Yet the same basic principle remains. Different materials respond differently to erosion, and whenever that happens, structure appears. One of the most fascinating aspects of the cosmic cliffs is the presence of pillars. These pillars often look like giant fingers reaching into space. Some appear narrow and delicate. Others seem massive and imposing. All of them tell the same story. At some point, the surrounding material eroded faster than the material inside the pillar. The pillar survived because it contained denser gas. Gravity helped hold it together. Radiation removed the less protected surroundings. Over millions of years, the contrast became increasingly dramatic. Eventually, a giant pillar emerged. The structure seems intentional, almost designed, yet it arises naturally from simple physical rules. This tendency for complexity to emerge from simple rules appears everywhere in astronomy. Galaxies form spirals, clouds create pillars, gravity builds stars. No central planner exists, no blueprint guides the process. Physical laws simply operate consistently. Given enough time, astonishing structures emerge. The cosmic cliffs provide one of the most beautiful examples. Another consequence of radiation-driven sculpting involves the creation of cavities. Earlier, we discussed how stellar winds can carve enormous bubbles into surrounding clouds. Radiation contributes as well. As gas becomes ionized and heated, it expands. The expansion pushes against neighboring material. Over time, hollow regions grow larger. Some cavities become enormous. Many span distances greater than the entire solar system. Others stretch across multiple light years. The resulting landscape begins to resemble Swiss cheese on a cosmic scale. Dense walls surround hollow interiors. Tunnels connect larger regions. Complex networks emerge. And because the process continues continuously, the architecture never stops evolving. Imagine being able to watch the Carina Nebula over millions of years. You would witness structures growing and shrinking, pillars collapsing, cavities expanding, new ridges appearing, old walls disappearing. The landscape would seem alive. Not alive in the biological sense, but active, dynamic, changing. The famous image captured by Webb represents only a single frame from that ongoing story, a snapshot taken during one brief moment in the life of the nebula. What makes the image especially powerful is that it reveals both the present and the future simultaneously. The visible structures tell us what radiation has already accomplished. The hidden regions tell us what may happen next, because many of the surviving dense pockets contain young stars still forming. Radiation is sculpting the cloud. Gravity is building stars. The two processes occur side by side. In fact, radiation sometimes acts almost like a gardener pruning a plant. This comparison may sound strange, but it captures something important. Pruning removes material, yet it can also encourage new growth. Similarly, radiation strips away gas from some regions while helping trigger collapse elsewhere. The destruction of one structure may create the conditions necessary for a new star. The relationship is surprisingly complicated. Astronomers once viewed radiation primarily as an obstacle to star formation. After all, if radiation removes gas, it reduces the material available for building stars. That logic remains valid. Yet observations revealed another side to the story. Compression caused by radiation can actually promote collapse. The cloud becomes denser, gravity strengthens, star formation begins. The same force that destroys one opportunity can create another. The universe rarely offers simple answers. Processes often produce multiple outcomes simultaneously. The cosmic cliffs showcase this beautifully. Everywhere scientists look, they find evidence of competing influences. Radiation removes material. Radiation compresses material. Gravity gathers material. Stellar winds redistribute material. The landscape emerges from the interaction of all these forces. One particularly interesting consequence involves timing. The giant stars responsible for sculpting the cliffs are relatively young, yet they are already changing their environment dramatically. Massive stars evolve quickly. Their intense energy output accelerates everything around them. Compared to smaller stars, they behave almost impatiently. They reshape their surroundings rapidly. They consume fuel rapidly. They live rapidly. The entire region feels more dynamic because of their presence. Without these giant stars, the cloud would evolve differently. More slowly, perhaps more quietly. Instead, the nebula becomes an active construction site. Energy flows everywhere. Structures change continuously. New stars emerge, and through it all, light remains one of the dominant sculptors. What's especially remarkable is that the same phenomenon operates throughout the Milky Way. The cosmic cliffs are not unique. They are spectacular. They are unusually well observed. But the underlying physics appears throughout the galaxy. Whenever massive stars form, radiation begins reshaping nearby clouds. Whenever clouds respond, new structures emerge. Whenever structures emerge, future generations of stars may follow. The cycle repeats endlessly, generation after generation, cloud after cloud, region after region. Looking at the cosmic cliffs, we are therefore seeing more than a beautiful photograph. We are seeing a universal process, a process that has operated for billions of years, a process that helped shape the birthplace of our own sun, a process still active throughout countless stellar nurseries. If you could somehow drift through the Carina Nebula and approach the towering structures of the cosmic cliffs, one thing would become clear very quickly. The most important activity isn't happening out in the open. The dramatic walls, the glowing ridges, the giant pillars stretching across space. These features are impressive, certainly. They're what first capture our attention. They're what made the James Webb Space Telescope image famous around the world. But they are only the visible surface of a much deeper story. The real action is hidden inside, buried within dense knots of gas and dust, concealed behind curtains of material that block ordinary light, protected from the harsh radiation flooding the surrounding nebula. Astronomers sometimes call these dense regions stellar cocoons. Others describe them as cores. Some are nicknamed stellar eggs. Whatever name is used, the idea remains the same. These are the places where stars are still growing. Places where gravity has gathered enough material to begin constructing entirely new suns. The comparison to eggs turns out to be surprisingly useful. An egg hides development from the outside world. Something important is happening inside, something alive, something changing. Yet until the shell breaks open, much of that activity remains concealed. The dense clouds inside the cosmic cliffs work in a similar way. Radiation from nearby giant stars bombards the outer layers. Powerful stellar winds sweep through the region. The environment is chaotic and energetic, Yet deep inside the densest pockets, young stars continue developing in relative isolation. The cloud acts as a shield, a protective barrier, a temporary shelter during the earlier stages of stellar life. One of the great achievements of the James Webb Space Telescope is that it allows astronomers to peer inside many of these stellar eggs more effectively than ever before. Visible light struggles to penetrate thick dust clouds. For decades, large portions of stellar nurseries remained hidden. Scientists knew something was happening there. They could detect clues. They could infer the presence of young stars. But much of the direct evidence remained obscured. It was like hearing activity behind a closed door without being able to see inside. Webb changed that. Because Webb observes primarily in infrared wavelengths, it can see through dust that blocks visible light. Suddenly, previously hidden regions become accessible. Structures emerge, young stars appear, entire populations of newborn stellar objects reveal themselves, and what astronomers discovered was extraordinary. The cosmic cliffs are crowded with stellar infants, not one or two, not dozens. Large populations of young stars occupy the region. Some are only beginning their development, others are further along. Many remain embedded inside dense clouds. Each one represents a future star. Each one is following a journey that began with a collapsing pocket of gas and dust. Yet no two journeys are identical. This is one of the most fascinating aspects of star formation. The overall process follows familiar physical laws. Gravity gathers material, clouds collapse, protostars emerge, fusion eventually begins. But the details vary enormously. Some stars accumulate large amounts of mass. Others remain relatively small. Some form alone. Many form with companions. Others emerge as members of larger clusters. Nature seems remarkably creative while following the same basic rules. Imagine visiting a forest filled with young trees. Every tree begins as a seed. Every tree grows according to similar biological principles. Yet no two trees develop in exactly the same way. Their surroundings differ. Available resources differ. Their histories differ. Stellar nurseries display similar diversity. Every young star begins with gravity. What follows depends on many factors. One particularly important factor is the amount of material available. The mass gathered during formation influences almost everything that comes afterward. A protostar with abundant material may become a massive star. Another may remain relatively modest. The difference matters enormously. Mass determines brightness, temperature, lifespan, future evolution, even the manner of death. A star's destiny begins taking shape very early, long before it becomes visible as a mature star. Inside these stellar eggs, the process remains surprisingly messy. Popular illustrations often show young stars as neat glowing spheres floating in darkness. Reality tends to be more complicated. Gas swirls chaotically. Magnetic fields twist through the cloud. Material falls inward. Jets shoot outward. Disks rotate around the growing protostar. The environment resembles a construction site more than a finished product, and construction can become quite dramatic. As material spirals toward the center of a forming star, enormous amounts of energy are released. The infalling gas heats up, shock waves develop, the surrounding disk becomes active. Sometimes powerful jets erupt from the poles of the protostar. These jets can travel hundreds of kilometers per second. Some eventually extend across distances larger than our solar system. Others stretch for light years. It's a curious sight. A star still being born, somehow launching streams of material into space. For many years, astronomers struggled to understand these jets fully. Today, observations suggest they play an important role in regulating growth. A forming star faces a challenge. Gravity continuously pulls material inward. Without some mechanism to remove excess angular momentum, growth becomes difficult. The jets help solve that problem. They act like release valves. Energy and momentum escape. The star continues developing. Nature often finds surprisingly elegant solutions to physical problems. Another remarkable feature hidden inside these stellar eggs is the presence of protoplanetary disks. These disks deserve special attention because they represent the birthplace of future worlds. Every major planet in our solar system originated within such a structure. Earth, Mars, Jupiter, Saturn, all began inside a rotating disk surrounding the young sun. The same process appears to be occurring throughout the cosmic cliffs. Around many newborn stars, disks of gas and dust continue orbiting. Within these disks, countless tiny particles collide. Dust grains stick together. Small clumps become larger clumps. Over time, larger structures emerge. The process takes millions of years, yet eventually entire planets may develop. When astronomers study a stellar nursery, they're often observing two creation stories unfolding simultaneously. Stars are forming. Planets are forming. The future architecture of solar systems is beginning to emerge, and because the cosmic cliffs contain so many young stellar objects, the possibilities become almost overwhelming. Some of these systems may eventually resemble our own solar system, others may look entirely different. Some may produce giant gas worlds orbiting close to their stars. Others may create rocky planets. Some systems may contain multiple stars, others only one. The diversity of outcomes reflects the diversity of starting conditions. The universe appears remarkably good at generating variety. Of course, not every stellar egg survives. This is another reality hidden beneath the beautiful imagery. Star formation is not guaranteed. Some collapsing clouds fail. Some lose material too quickly. Radiation from nearby giant stars can disrupt development. Stellar winds can strip away gas. Competition for material can affect growth. The environment remains challenging. Imagine trying to build a house during a constant storm. Construction becomes difficult. Some projects succeed, others do not. The cosmic cliffs present similar challenges. The giant stars surrounding the region continuously flood it with energy. Their radiation penetrates exposed areas. Their winds reshape the cloud. The stellar eggs survive only because their dense outer layers provide protection. But that protection is temporary. Eventually the cocoon begins disappearing. Radiation erodes it. Winds remove material. The surrounding cloud gradually thins. At some point the young star emerges. Astronomers sometimes compare this moment to hatching. The analogy works surprisingly well. A developing star spends part of its early life hidden inside a protective environment. Then the environment disappears. The star becomes visible. Its independent life begins. Throughout the Carina Nebula, countless examples exist at different stages. Some stars remain deeply embedded. Others are partially exposed. Still others have fully emerged. Together they create a timeline of stellar birth spread across space. Instead of watching one star form over millions of years, astronomers observe many stars at different stages. The result resembles flipping through a cosmic photo album. Each object reveals a different chapter in the story. One image shows the beginning. Another shows growth. Another shows emergence. Combined, they reveal the larger process. What's especially fascinating is that these hidden stars are not merely future sources of light. They are future sources of change. Eventually, many will begin influencing their surroundings, just as today's giant stars influence the cosmic cliffs. They will emit radiation. They will produce stellar winds. Some may eventually explode as supernovae. The next generation will help shape the generation after that. The cycle never truly stops. A stellar nursery is therefore more than a birthplace. It is part of a continuing chain stretching across billions of years. Older stars create conditions for younger stars. Younger stars eventually become older stars. The process repeats endlessly. The material itself gets recycled. Atoms move from cloud to star, from star to cloud, from one generation to the next. The carbon in future planets may currently reside inside a protostellar disk. The oxygen in a future atmosphere may still be hidden within a dense cloud. The story remains unfinished. The ingredients are present. The outcome remains unknown. Looking at the cosmic cliffs, it's easy to become captivated by the giant visible structures, yet the hidden stellar eggs tell an even deeper story. Inside those dense pockets, gravity continues working quietly. Protostars continue growing. Future solar systems continue taking shape. Entire possibilities remain concealed within the dust. A stellar nursery may look chaotic from a distance. Clouds stretch across light years. Radiation floods through space. Stellar winds carve enormous cavities. Gravity pulls material inward. Newborn stars appear in clusters. At first glance, it can seem as though stars simply emerge wherever enough gas happens to collect. Yet when astronomers study these regions carefully, they encounter a puzzling reality. Not every cloud becomes a star. In fact, many do not. Throughout the cosmic cliffs and the larger Carina Nebula, vast amounts of gas and dust are present. Some regions are actively forming stars. Others appear remarkably quiet. Some dense clouds collapse successfully. Others resist collapse for millions of years. A few may never produce stars at all. This raises an obvious question. If gravity is always pulling, why doesn't every cloud eventually collapse? The answer turns out to be one of the most fascinating balancing acts in astronomy. Because gravity is powerful, but gravity is not alone. Every cloud exists within a constant tug-of-war between forces trying to pull material together and forces trying to keep it apart. Whether a star forms depends on which side wins. Imagine placing a pile of sand on the ground. Gravity pulls every grain downward. Left alone, the pile settles into a stable shape. Now imagine trying the same thing underwater, while currents push in different directions. Suddenly the situation becomes more complicated. Multiple influences compete. The final result depends on their balance. Molecular clouds face a similar challenge. Gravity continuously tries to gather material. At the same time, other processes push back. Heat, turbulence, magnetic fields, radiation, stellar winds. All of these can resist collapse. The cloud becomes a battleground, and not every region wins the battle. To understand this, we need to start with density. Density plays an enormous role in determining a cloud's future. Gravity becomes more effective when material is concentrated. A diffuse cloud may contain tremendous amounts of gas, but if that gas is spread across a large volume, gravitational attraction remains relatively weak. The cloud can persist for long periods without collapsing. A denser region behaves differently. More mass occupies less space. Gravity strengthens. Material begins gathering more efficiently. Collapse becomes increasingly likely. This seems straightforward, yet nature rarely keeps things simple. Because density alone does not guarantee success. Temperature matters too. A cloud may possess substantial density while remaining too warm for gravity to dominate. Heat creates pressure. Pressure pushes outward. The warmer the gas becomes, the more strongly it resists compression. In effect, the cloud develops a defense mechanism against gravity. The relationship resembles inflating a balloon. The air inside pushes outward. Squeezing the balloon becomes harder because pressure resists compression. Gas clouds behave similarly. Gravity squeezes inward. Pressure pushes outward. The outcome depends on which influence becomes stronger. Many clouds spend millions of years balancing between these competing forces. Neither side fully wins. The cloud survives. Star formation remains delayed. Astronomers often describe such clouds as being in a state of near equilibrium. Not perfectly stable, but stable enough. Then something changes. Perhaps a nearby supernova sends a shockwave through the region. Perhaps stellar winds compress part of the cloud. Perhaps collisions between clouds increase density. A small shift occurs. The balance tips. Gravity gains an advantage. Collapse begins. One reason the cosmic cliffs fascinate astronomers is that they contain examples of clouds occupying many different stages of this process. Some regions have already collapsed, others appear close to collapse. Still others remain relatively stable. Together they provide a laboratory for understanding why star formation happens where it does, and why it doesn't happen elsewhere. Another important factor is turbulence. When most people hear the word turbulence, they think of airplane flights. A smooth journey suddenly becomes bumpy. Passengers grip armrests. Coffee becomes slightly more dangerous. Inside molecular clouds, turbulence operates on vastly larger scales. Gas moves in complex patterns. Streams collide. Shock waves travel through the cloud. Different regions move at different speeds. The result can either help or hinder star formation. Sometimes turbulence compresses gas. Dense pockets emerge. Gravity takes over. Star formation begins. Other times turbulence disperses material. Potential star-forming regions break apart. Collapse gets delayed. The same process can produce opposite outcomes depending on circumstances. Nature frequently behaves this way. The effect depends on context. Magnetic fields introduce another layer of complexity. These fields permeate much of the interstellar medium. Though invisible, they influence the motion of charged particles and affect the behavior of gas clouds. For decades, astronomers have investigated how magnetic fields impact star formation. The answer appears to be significant. Strong magnetic fields can help support clouds against gravitational collapse. They act like invisible scaffolding. Material still moves, gravity still operates, but collapse becomes more difficult. Eventually gravity may overcome the resistance, or it may not. Again, the outcome depends on balance. The universe seems remarkably fond of balance. Over and over, astronomers discover systems existing near critical thresholds. A little more density, a little less pressure, a slight increase in compression, a small decrease in turbulence. Tiny differences can determine whether a cloud remains a cloud or becomes a star. One particularly useful concept is something called the Jeans instability. Named after the British physicist Sir James Jeans, it describes the conditions under which a cloud becomes unstable and begins collapsing under its own gravity. The idea is surprisingly elegant. Every cloud has a critical size and mass. Below that threshold, pressure can resist gravity. Above it, gravity gains the upper hand. Collapse becomes inevitable. Imagine stacking books. A small stack remains stable. Add enough books, however, and the structure may become unstable. At some point, a threshold is crossed. The same principle applies to molecular clouds. When enough material gathers within a sufficiently small volume, stability disappears. Gravity wins. A future star begins taking shape. Inside the cosmic cliffs, countless regions have crossed this threshold. Others have not. That difference explains much of what astronomers observe. Some dense knots contain protostars. Nearby knots remain inactive. The environments appear similar. The outcomes differ dramatically. Because one region crossed the threshold while another remained below it. Yet even crossing the threshold doesn't guarantee identical results. Competition often emerges. A giant molecular cloud may begin fragmenting into multiple dense cores. Instead of producing one massive star, the cloud creates many smaller stars. Gravity pulls material towards several centers simultaneously. Each core competes for available gas. The final distribution determines the future population of stars. This fragmentation process helps explain why stars frequently form in clusters. The cloud doesn't collapse into a single object, it breaks apart. Multiple stars emerge. The cosmic cliffs contain numerous examples. Young stars appear in groups rather than isolation. Families of stars grow together. Some remain gravitationally connected for long periods. Others eventually drift apart. The cluster disperses. The stars continue their lives separately. Our own sun may have experienced something similar. Astronomers believe the Sun probably formed within a larger stellar cluster billions of years ago. Its siblings have since scattered throughout the Milky Way. Finding them today is extraordinarily difficult, yet the evidence suggests the Sun was not born alone. Like many stars, it likely emerged from a crowded nursery. The same pattern appears throughout the Carina Nebula. Clusters form, groups emerge, the cloud fragments into multiple stellar seeds. Radiation introduces yet another complication. Throughout the cosmic cliffs, giant stars flood the environment with ultraviolet light. This radiation can suppress star formation by eroding clouds. Material gets removed. Potential stellar seeds disappear. Yet radiation can also trigger star formation. Compression increases, density rises, collapse begins. Astronomers sometimes refer to this as triggered collapse. A nearby massive star effectively nudges a cloud across the critical threshold. Without the radiation, the cloud might remain stable. With the radiation, it collapses. A new star forms. This dual role makes radiation particularly fascinating. It acts as both creator and destroyer. One cloud gets dispersed, another becomes compressed. One opportunity vanishes, another appears. The outcome depends on local conditions. No single rule applies everywhere. This complexity helps explain why star formation remains one of astronomy's most active research areas. The basic principles are understood. Gravity gathers material. Dense regions collapse. Stars emerge. Yet predicting exactly which clouds will succeed remains challenging. Real stellar nurseries contain countless interacting factors. Every cloud possesses its own history. Every region experiences unique influences. The details matter. And that's part of what makes the cosmic cliff so valuable scientifically. The region contains many clouds occupying different stages of development. Some are clearly forming stars, others appear dormant. Some may eventually collapse, others may never do so. By studying these differences, astronomers gain insight into the conditions required for stellar birth. The observations reveal something else as well. Star formation is surprisingly inefficient. Only a fraction of the gas inside a giant molecular cloud ultimately becomes part of stars. The majority remains behind. Radiation disperses it. Winds redistribute it. Some material escapes entirely. Nature is not trying to maximize efficiency. Nature is simply following physical laws. The result happens to be messy. Clouds lose material. Stars gain material. The balance shifts continuously. And throughout the process, chance plays a role. Not randomness in the everyday sense, but sensitivity to initial conditions. Small differences grow larger over time. A slightly denser region gains an advantage. A slightly stronger shockwave triggers collapse. A slightly weaker magnetic field allows gravity to dominate. Tiny variations influence enormous outcomes. Future stars depend on subtle beginnings. Looking across the cosmic cliffs, astronomers therefore see more than a beautiful landscape. They see a collection of possibilities. Some clouds are becoming stars, others are resisting, some futures are taking shape, others are fading away. The entire region functions as a giant experiment conducted by nature itself. Not every childhood is peaceful. For human beings, childhood often brings images of learning, growth, and gradual development. We picture classrooms, playgrounds, family homes, and years spent slowly becoming adults. Stars experience something rather different. The early life of a star unfolds inside one of the most chaotic environments in the universe. Violent radiation floods through space. Shock waves race across enormous distances. Supersonic winds carve through clouds. Nearby stars compete for material. Entire regions collapse under gravity while neighbouring regions are blasted apart. Far from being calm nurseries, stellar nurseries are some of the most turbulent places in the galaxy, and nowhere is that easier to see than within the Carina Nebula. Looking at the famous image of the cosmic cliffs, It's easy to forget this. The photograph feels peaceful. The glowing ridges seem quiet. The giant walls appear almost serene. Viewed from Earth, the region resembles a frozen landscape, a still moment captured in time. But that impression is misleading. The apparent calm exists only because astronomical timescales are so vast. Human lives unfold too quickly to witness most of the motion. If we could somehow accelerate time by millions of years, the entire region would look dramatically different. Clouds would expand and contract. Pillars would shrink. Cavities would grow. Stars would ignite. Shock fronts would sweep across the nebula. The landscape would seem alive with activity. The cosmic cliffs would resemble a dynamic weather system operating across light years of space, and at the centre of much of this activity are young stars themselves. Ironically, the very stars being born inside the nursery quickly begin making life more difficult for their neighbours. The moment a sufficiently massive star ignites nuclear fusion, it starts changing everything around it. Radiation floods outward. Stellar winds begin blowing. Gas heats up. Clouds respond. The newborn star immediately becomes an environmental force. It doesn't wait. It doesn't gradually ease into adulthood. It announces its arrival to the surrounding nebula with tremendous energy. Imagine a quiet neighbourhood suddenly gaining a resident who operates industrial machinery 24 hours a day. The entire area would change. Now imagine thousands of such residents arriving simultaneously. That comparison still falls far short of what happens inside a stellar nursery. The energy involved is vastly greater. One of the most dramatic examples involves ultraviolet radiation. Massive young stars produce enormous quantities of it. This radiation spreads outward in all directions. When it encounters nearby gas clouds, it begins stripping electrons from atoms. The gas becomes ionized. Temperatures rise. Pressure increases. Material starts moving. The cloud reacts. For young stars hidden inside dense regions, this can create serious challenges. A developing star depends on surrounding material. Gas continues falling inward. The protostar continues growing. The larger the available reservoir, the more massive the eventual star may become. But nearby giant stars can interfere. Radiation may erode the surrounding cloud. Material gets stripped away before it reaches the growing protostar. The future star effectively loses access to part of its food supply. Astronomers sometimes describe this process as photoevaporation. The name sounds surprisingly gentle. The reality is not. Powerful radiation essentially boils material away from the cloud. Gas escapes. Dense structures shrink. Potential future stars lose resources. The effect can dramatically alter development. Some protostars may never become as massive as they otherwise would have. Others may stop growing entirely. The neighbourhood becomes competitive. Resources are limited. Conditions are harsh. And radiation is only one problem. Stellar winds create another. Throughout the Carina Nebula, giant stars continuously launch streams of charged particles into space. These winds travel at extraordinary speeds, hundreds, sometimes thousands, of kilometers per second. When they collide with surrounding gas, shock waves form. The resulting interactions can compress clouds, disrupt clouds, or completely reshape portions of the nebula. For young stars still embedded within dense regions, these winds create additional uncertainty. A stable environment may suddenly become unstable. Gas distributions change, pressure conditions shift, the surrounding cloud evolves. The stellar nursery remains in constant motion. This combination of radiation and stellar winds means that many young stars spend their earliest years inside a changing environment. The conditions present when collapse begins may not remain present for long. The neighbourhood evolves around them, sometimes rapidly by astronomical standards. One particularly fascinating consequence involves what astronomers call triggered star formation. At first glance, the phrase sounds contradictory. If radiation and stellar winds are disruptive, how can they help create stars? The answer lies in compression. When expanding shock fronts encounter a cloud, they squeeze it. Density increases, gravity gains strength, collapse becomes easier. A region that previously remained stable may suddenly begin forming stars. The same forces that destroy one cloud can create another generation of stars elsewhere. The process resembles a forest fire in some respects. A fire destroys existing vegetation. Yet afterward, new growth often emerges. Destruction and creation become linked. Stellar nurseries operate similarly. One generation influences the next. The birth of one star may contribute to the birth of another. The cycle repeats continuously. Inside the cosmic cliffs, astronomers observe evidence of this process everywhere. Some regions appear heavily eroded, others show signs of recent compression. Still others contain populations of extremely young stars likely influenced by nearby stellar activity. The entire landscape records a history of interaction. Nothing develops in isolation. Every object influences its surroundings. Every change creates additional changes. The complexity becomes extraordinary. Another challenge facing young stars involves competition. Popular depictions sometimes show a star forming alone inside a cloud. While this certainly happens, many stars emerge in crowded environments. Clusters form. Multiple protostars develop simultaneously. Each one draws material from the surrounding cloud. Each one influences neighbouring objects. The situation resembles several growing plants sharing the same patch of soil. Resources become important. Position matters, timing matters. Some stars gain access to more material, others receive less. The differences can become significant. A protostar forming in a favourable location may accumulate far more mass than one developing nearby. The outcomes diverge. One becomes large and luminous, another remains relatively small. Tiny initial advantages grow into major differences over time. Astronomers see this repeatedly throughout stellar nurseries. The environment shapes destiny, not completely but significantly. And then there are the jets. Earlier we discussed how many young stars launch powerful streams of material from their poles. These jets represent some of the most dramatic features associated with stellar birth. They can extend enormous distances. They move at remarkable speeds. They slam into surrounding gas. Shock fronts appear. Complex structures emerge. For the young star, the jets help regulate growth. For the surrounding environment, they introduce additional turbulence. The nursery becomes even more active. Imagine dozens or hundreds of young stars simultaneously firing jets into a shared cloud. The resulting environment becomes incredibly complicated. Gas moves in multiple directions. Pressure changes constantly. Shock waves overlap. The cloud evolves. Astronomers studying regions like the Carina Nebula must account for all these interacting processes. Gravity, radiation, stellar winds, jets, magnetic fields, turbulence, each contributes to the larger story. One of the reasons the James Webb Space Telescope created such excitement is that it revealed many of these features in unprecedented detail. Hidden jets became visible, young stellar objects appeared, structures previously obscured by dust emerged. Scientists gained a clearer view of the complex interactions shaping the region, and what they found reinforced an important lesson. Star formation is not neat. It is not orderly. It is not gentle. The word nursery sometimes creates the wrong impression. Human nurseries are designed to protect growth. Stellar nurseries produce growth through chaos. The environment remains active from beginning to end. Yet despite all this apparent violence, stars continue forming successfully. This is perhaps the most remarkable aspect of the process. The obstacles are enormous. The environment is challenging. Radiation strips material away. Shockwaves reshape clouds. Competition limits resources, and still gravity keeps working. Protostars continue growing. Fusion eventually ignites. New stars emerge. Nature proves remarkably persistent, even in difficult conditions, perhaps especially in difficult conditions. Over millions of years, entire populations of stars arise from these turbulent environments. Some become red dwarfs, others resemble the Sun. A few grow into giant stars that eventually reshape the next generation of clouds. The cycle continues. The nursery remains active. Several thousand years ago, the light currently reaching Earth from the cosmic cliffs was just beginning its journey. Back then, the stars hidden inside the nebula were already forming. Dense clouds were already collapsing. Radiation was already sculpting the landscape. And perhaps most remarkably of all, some of those newborn stars were already beginning to build something else, something smaller than stars, something easier for us to relate to, future worlds. When people first learn about stellar nurseries, it's natural to focus on the stars. After all, stars dominate the story. They illuminate galaxies, they power planetary systems, they shape the evolution of the universe around them. Yet stars are only part of the outcome. Whenever a star forms, another process often begins alongside it. A quieter process, a slower process, a process that eventually creates planets. The two stories are inseparable. You cannot truly understand one without understanding the other. And that means the cosmic cliffs are not merely a birthplace for future stars. They are a birthplace for future solar systems, perhaps even future Earth-like worlds, perhaps future oceans, perhaps future skies, perhaps places where living creatures will one day look upward and wonder where they came from. To understand how this happens, we need to return briefly to the moment a star is forming. As gravity pulls gas inward, the collapsing cloud doesn't simply fall straight toward the center. Almost every cloud possesses at least a tiny amount of rotation. Usually this rotation is extremely slow, perhaps so slow that it would be impossible to notice without careful measurements. But nature has a habit of amplifying small effects. As the cloud contracts, that rotation speeds up. The process follows the same principle that causes an ice skater to spin faster when pulling their arms inward. Astronomers call this conservation of angular momentum. The name sounds technical. The result is simple. A rotating disk forms around the growing protostar. This disk becomes one of the most important structures in astronomy, because the disk is where planets begin. Inside the cosmic cliffs, countless disks likely surround young stars hidden within the dust. Some are large, some are small, some may already be developing planetary building blocks, others remain in very early stages. Together they represent future possibilities scattered throughout the nebula. The disk itself begins as a mixture of gas and microscopic dust particles. At first glance, dust sounds rather unimpressive. We spend much of our lives trying to remove dust from things. Furniture, shelves, computer screens. The universe, however, treats dust very differently. Cosmic dust is extraordinarily important. Without it, planets like Earth would never exist. The dust inside stellar nurseries contains tiny grains made from heavier elements: carbon, silicon, oxygen, iron, magnesium, elements forged inside earlier generations of stars. In a sense, every grain of dust carries a history. A previous generation of stars lived, created heavy elements, died, released those elements into space. Eventually those materials became part of a new cloud, and now they find themselves inside a disk surrounding a newborn star. The universe recycles remarkably well. Over time, collisions occur within the disk. Tiny particles strike one another. Sometimes they bounce apart, sometimes they stick together. The sticking is important, because once particles begin clumping, growth accelerates. Small grains become larger grains. Larger grains become pebbles. Pebbles become rocks. Rocks become larger bodies. Eventually, objects kilometers across may emerge. Astronomers call these planetesimals. The name sounds somewhat awkward, but it describes exactly what they are. Small planetary building blocks, future planets in their earliest recognizable form. One of the astonishing things about this process is how much complexity emerges from simple beginnings. No one assembles a planet. No cosmic engineer supervises construction. No blueprint exists. Particles collide. Gravity operates. Time passes. The system gradually organizes itself. Nature builds worlds through countless small interactions. Given enough time, entire planetary systems emerge. Our own solar system followed this path roughly 4.6 billion years ago. The young sun sat at the centre, a rotating disk surrounded it. Dust grains collided, planetesimals formed. Those planetesimals merged repeatedly. Some grew into planets, others became moons, some remained as asteroids, some became comets. The architecture we see today gradually developed from those early conditions. Looking at the cosmic cliffs is therefore a bit like looking backward in time at our own origins, not literally. The Carina Nebula is not the birthplace of the Sun, but the physical processes appear remarkably similar. The same laws operate, the same ingredients exist. Gravity gathers material, stars form, disks emerge, planets begin developing. The recipe remains familiar. One of the most exciting discoveries in modern astronomy is that planetary systems appear to be common. For much of human history, we had only one example, our own solar system. Without additional examples, it was difficult to know whether planetary systems were rare or abundant. Perhaps the Sun was unusual. Perhaps planets formed only under special circumstances. Perhaps Earth occupied a unique position in the universe. Then astronomers began discovering exoplanets, planets orbiting other stars. At first the discoveries arrived slowly, one here, another there. Then the numbers increased, hundreds, thousands. Today, astronomers have confirmed thousands of exoplanets, and the evidence strongly suggests that countless more remain undiscovered. Planetary systems appear to be common throughout the Milky Way. This realization changes how we view stellar nurseries. Every young star becomes a potential host. Every protoplanetary disk becomes a potential birthplace. Every dense cloud may eventually contribute to new worlds. The cosmic cliffs therefore contain not only future stars but potentially future planetary systems by the thousands. Some of those systems may be strange beyond imagination. Astronomers have already discovered planets unlike anything in our solar system. Worlds larger than Jupiter orbiting extremely close to their stars. Planets covered by deep oceans. Planets with years lasting only a few days. Planets orbiting multiple stars. Planets where temperatures exceed thousands of degrees. Nature appears remarkably inventive. There is little reason to assume future systems forming inside the cosmic cliffs will resemble our own perfectly. Many likely won't. Different stars create different environments. Different disks produce different outcomes. Small changes during formation can lead to enormous differences later. A slightly more massive disk, a slightly different chemical composition, a nearby stellar encounter, a burst of radiation. Tiny variations may influence the final result. This diversity is one reason planetary science remains so fascinating. The universe is constantly conducting experiments. Every new solar system represents another outcome, another possibility explored, another arrangement of matter shaped by gravity and time. Yet despite all this variety, certain patterns continue appearing. Rocky worlds often form closer to stars. Gas giants frequently develop farther away. Moons emerge around planets. Asteroids remain as leftovers. The details vary. The general process repeats. It's a bit like baking. Different bakers produce different results. Ingredients vary. Techniques vary. Outcomes vary. Yet certain underlying principles remain recognizable. Planetary formation works similarly. The details change. The physics remains. Inside the cosmic cliffs, many young stars are probably surrounded by disks currently undergoing these early stages. The process remains hidden from direct view in many cases. Dust obscures the details. The systems remain extremely young. Yet astronomers can identify clues. Infrared observations reveal warm disks. Spectroscopy reveals chemical compositions. Jets indicate active accretion. Each observation helps reconstruct the story. The picture that emerges is remarkable. The nebula contains future possibilities everywhere. Some disks may eventually disappear without producing major planets. Others may generate entire families of worlds. A few could create environments suitable for life. At this stage, nobody knows. The future remains unwritten. The ingredients are present. The outcomes are still developing. Another fascinating aspect involves timing. Planet formation begins surprisingly early. For many years, astronomers debated exactly when planets start forming. Recent observations increasingly suggest the process may begin almost immediately after stellar birth. The clock starts early. Dust grains begin interacting. Structures emerge. Growth accelerates. The universe wastes little time. As soon as conditions allow, complexity begins developing. This means some of the young stars hidden inside the cosmic cliffs may already possess the earlier seeds of future planets. Not completed planets, not recognizable worlds, but the first building blocks, the first steps, the earlier stages of a process that could eventually produce continents, atmospheres, oceans, and perhaps much more. The thought is difficult to ignore. Somewhere inside those clouds, future worlds may already be taking shape. Future landscapes, future weather systems, future skies, places that currently exist only as scattered grains of dust orbiting a newborn star. And all of this remains connected to a larger cycle, because the material inside those disks did not appear from nowhere. It originated in older stars. The carbon, oxygen, silicon and iron were forged long ago. The previous generation created them. The current generation inherits them. Future generations will inherit them again. The universe functions as a continuous chain of recycling and renewal. Stars create elements. Elements form planets. Planets become part of future clouds. New stars emerge. The process continues. The cosmic cliffs provide a snapshot of one stage within that immense cycle. A place where old material is becoming new systems, where future solar systems are quietly assembling themselves inside clouds of dust, where the next generation is already beginning. One of the easiest mistakes to make when looking at a place like the cosmic cliffs is to think of it as something distant. Not merely distant in space, distant in relevance, distant in meaning. After all, the cliffs lie roughly 7,600 light-years away. They exist inside a giant nebula most people had never heard of before the James Webb Space Telescope released its famous image. The stars forming there belong to another region of the galaxy, another environment, another story. At first glance, it seems to have very little to do with us. And yet, the deeper astronomers investigate stellar nurseries like the cosmic cliffs, the more they discover something surprising. The story unfolding there is not entirely different from our own story. In fact, many of the processes occurring inside those clouds almost certainly occurred before the sun existed, before Earth formed, before the oceans appeared, before life emerged, long before human beings looked up at the stars and wondered where they came from. The cosmic cliffs are not merely showing us how stars form, they are showing us how we formed, not directly, not literally, but through the same physical processes that ultimately made our existence possible. To understand why, we need to travel backward in time. Not thousands of years, not millions, billions. Roughly 4.6 billion years ago, our solar system did not exist. There was no Earth, no Moon, no Jupiter, no Saturn, no Sun. The familiar arrangement of planets and worlds we know today had not yet appeared. Instead, there was a cloud, a giant cloud of gas and dust drifting through part of the Milky Way. Somewhere within that cloud, conditions began changing. Gravity started gathering material, dense regions formed, collapse began, the cloud evolved, and eventually one particular region became the birthplace of our sun. Astronomers cannot point to the exact location today. The original stellar nursery disappeared long ago. Its structure dissolved, Its stars drifted apart, its clouds dispersed into the wider galaxy. Yet the evidence suggests that our solar system began inside an environment remarkably similar to the cosmic cliffs. Not identical. No two stellar nurseries are identical, but similar enough that studying one helps us understand the other. This realization changes how we view the famous Webb image. Instead of looking at an alien landscape disconnected from our lives, we begin looking at something close to an ancient family photograph. Not a photograph of our actual birthplace, but perhaps a photograph of a place that looked very much like it. A place where similar forces operated. A place where similar events unfolded. A place where future worlds were taking shape. One of the strongest clues comes from the chemistry of our solar system. The atoms that make up Earth tell a story. A surprisingly detailed story. Every atom has a history. Hydrogen formed shortly after the Big Bang, but many heavier elements did not. Carbon, oxygen, silicon, iron, calcium, gold, uranium. These elements required stars, specifically earlier generations of stars. Inside stellar cores, nuclear fusion gradually produced heavier elements. Massive stars created many of the ingredients needed for planets and life. When those stars eventually died, they released those elements into space. The material mixed with giant clouds of gas and dust. New stars formed from the enriched material. The cycle repeated. Eventually, some of that recycled matter became part of the cloud that formed our solar system. This means the atoms inside your body existed long before Earth, long before the sun, the calcium in your bones, the oxygen you breathe, the iron in your blood. All of it originated elsewhere. Much of it was manufactured inside stars that lived and died before our solar system existed. The phrase, "we are made of stardust," sometimes gets repeated so often that it risks sounding poetic rather than scientific, yet it is scientifically accurate. The statement reflects a real physical history. Without earlier generations of stars, many of the elements required for life would not exist. The cosmic cliffs remind us that this process is still happening. The next generation of stars is forming there. The next generation of planetary systems is beginning there. Future worlds are being assembled from material inherited from previous generations, exactly the same pattern that eventually produced Earth. Another clue comes from radioactive isotopes found in ancient meteorites. Meteorites are fascinating objects because many preserve material from the earliest history of the solar system. Some formed before planets existed. Some contain records dating back to the very beginning. When scientists analyze these ancient rocks, they find evidence suggesting that a nearby massive star may have influenced the formation of our solar system. Perhaps a supernova exploded near the cloud that became the sun. Perhaps the shockwave helped trigger collapse. The details remain debated. The evidence remains incomplete. Yet many astronomers believe our solar system formed in a crowded stellar environment rather than complete isolation. That possibility matters, because crowded stellar environments resemble places like the Carina Nebula. They contain massive stars. Radiation, shock waves, compression, triggered star formation. The same processes operating within the cosmic cliffs today. In other words, the environment that helped create us may have looked surprisingly similar to the environment Webb has revealed. This connection becomes even more interesting when we consider the Sun itself. The Sun often feels unique because it is our star. Every sunrise reinforces that impression. Every warm day reminds us of its importance. Yet astronomically speaking, the Sun is relatively ordinary. Not small, not large, not unusually bright, not unusually dim. It occupies a middle ground, the kind of star that appears frequently throughout the Milky Way. And stars like the Sun continue forming inside stellar nurseries across the galaxy. Some are forming inside the cosmic cliffs right now. Young stars hidden inside dense clouds may eventually resemble the Sun remarkably closely. Some may possess similar masses, similar temperatures, similar lifespans, similar planetary systems. Looking at those developing stars is therefore a bit like looking backward in time. We see stages our own star once experienced. The Sun was once a protostar. The Sun once possessed a protoplanetary disk. The Sun once sat inside a cloud of gas and dust. The familiar star lighting Earth today began its existence as a hidden object buried inside a stellar nursery. Exactly the sort of object astronomers now observe throughout the cosmic cliffs. The connection extends even further. Consider Earth itself. Everything about our world depends on its origins, its atmosphere, its oceans, its continents, its chemistry, its ability to support life. All trace back to events occurring during the solar system's formation. Tiny differences could have produced dramatically different outcomes. A slightly different orbit, a slightly different amount of water, a different arrangement of giant planets. Small changes during formation might have altered Earth's entire history. The same principle applies to the systems currently forming inside the cosmic cliffs. Their futures remain unwritten. Some may develop rocky planets, some may create gas giants, some may never produce stable planetary systems. Others could eventually host environments favourable for life. The possibilities remain open. The clouds contain ingredients, not outcomes. Watching a stellar nursery is therefore a little like watching the opening pages of a story. The ending remains unknown. The characters have only just appeared. The major events lie far in the future, yet the foundations are already being established. Another remarkable lesson emerges from this perspective. Human beings often think of themselves as separate from the universe. The universe exists out there. We exist here. The distinction feels natural. Yet the cosmic cliffs challenge that idea. The same physical laws shaping those clouds shaped Earth. The same gravity operating there operates here. The same atoms drifting through the nebula exist inside our bodies. The same processes that built future stars once helped build our Sun. The connection is continuous, not metaphorical, physical, real. This realization does not make the universe smaller. If anything, it makes it larger. Because it reveals how deeply connected different parts of cosmic history actually are. The story did not begin with Earth. It did not begin with humanity. It did not even begin with the Sun. The chain stretches backward through previous generations of stars, through ancient clouds, through billions of years of stellar evolution. The cosmic cliffs represent one link in that chain, a current chapter in a story that began long before us and will continue long after us. There's something humbling about that perspective. The cliffs seem enormous, the distances seem overwhelming, the timescales seem impossible to fully grasp, and yet the processes unfolding there helped make our existence possible. Not specifically those particular cliffs, but environments like them. Generations of stellar nurseries, generations of stars, generations of planetary systems. Without those cycles, Earth would never have formed, life would never have appeared, human beings would never have existed to wonder about any of it. Looking at the cosmic cliffs, therefore, becomes more than an exercise in astronomy. It becomes an opportunity to see our own origins reflected in another part of the galaxy. A reminder that the story unfolding there is not entirely separate from the story unfolding here. The stars forming inside those clouds are participating in the same grand cycle that eventually produced the Sun, Earth, and every living thing that has ever existed on our world. For a long time, human beings believed the stars were permanent. Night after night the sky appeared unchanged. The same constellations returned. The same bright points crossed the darkness. The stars seemed eternal, fixed, unchanging. It was an understandable conclusion. After all, a human lifetime is short compared to the lifetime of a star. Even civilizations come and go in the time it takes most stars to age noticeably. The universe moves on timescales that rarely match our own, and because of that, the deeper story remained hidden for most of history. We could see the stars, What we couldn't see was where they came from. Tonight, we've travelled to one of those places, not a place marked on any map, not a destination anyone will ever visit, but a place where one of the universe's oldest stories continues to unfold, the cosmic cliffs, a region of gas and dust roughly 7,600 light-years away. A landscape that isn't really a landscape, a wall that isn't really a wall, a mountain range made not of stone but of matter waiting to become something new. When the James Webb Space Telescope first revealed this region, millions of people saw beauty. They saw glowing ridges, towering pillars, vast caverns illuminated by distant stars. And the image truly is beautiful. But as we've discovered, the beauty is only the beginning. Hidden behind those cliffs lies an entire cycle of creation. Gravity quietly gathering material, dense clouds collapsing, protostars forming inside cocoons of dust, radiation carving giant structures into the nebula, young stars shaping the next generation, future solar systems beginning their long journey toward existence. Every part of the landscape tells a story. Every ridge records a history. Every pillar reveals a struggle between gravity and radiation. Every dense cloud contains possibility. The remarkable thing is that no one designed any of it. No blueprint exists. No cosmic architect oversees construction. The universe accomplishes everything through a handful of simple rules. Gravity pulls, radiation pushes, matter moves, time passes. Given enough time, complexity emerges. Stars appear, planets form, entire worlds come into existence. The same principles that operate inside the cosmic cliffs operate throughout the galaxy, and not just throughout the galaxy, throughout much of the observable universe. Wherever large clouds of gas gather, gravity begins its patient work. Wherever stars ignite, radiation begins reshaping the environment. Wherever matter accumulates, new possibilities emerge. The process repeats endlessly, generation after generation, cloud after cloud, galaxy after galaxy. One reason astronomers find stellar nurseries so fascinating is that they allow us to witness beginnings. Most of the objects we see in the universe are already mature. The Earth is mature, the Sun is mature. Most visible stars have existed for millions or billions of years. Even entire galaxies often appear fully developed. Beginnings are harder to find, yet beginnings matter, because they explain everything that follows. If you want to understand a forest, it helps to understand seeds. If you want to understand a river, it helps to understand its source. And if you want to understand stars, planets, and life itself, it helps to understand stellar nurseries. The cosmic cliffs provide exactly that opportunity, a glimpse into the earliest stages of a process that eventually creates entire solar systems, including systems that may one day resemble our own. Somewhere inside those clouds, stars are currently forming, not in the distant past, not merely in theory, right now. As you listen to these words, gravity continues pulling material inward. Protostars continue growing. Disks continue rotating around young stars. Dust grains continue colliding. The earliest ingredients of future worlds continue gathering together. The universe is still creating. That fact alone is extraordinary. Sometimes it's easy to imagine the universe as finished, a completed structure, a vast collection of stars simply existing in darkness. The cosmic cliffs remind us otherwise. The universe remains active. The story continues. New stars are still appearing. New planetary systems are still developing. Entire futures are still being assembled. And because of the immense timescales involved, much of that future remains hidden from us. The stars forming inside the cliffs today may continue shining long after human civilization has changed beyond recognition. Some may survive for billions of years. A few smaller stars may survive for trillions. Their stories have barely begun. The cliffs themselves will not last forever. This may be one of the most surprising lessons of all. The structures seem permanent. The ridges appear timeless. The pillars look ancient, yet they are temporary. Radiation continues eroding them. Stellar winds continue reshaping them. The landscape evolves continuously. Millions of years from now, the famous image captured by Webb will no longer represent reality. The cliffs will have changed. Some structures will disappear, others will emerge. New stars will illuminate the region. The nursery will continue evolving. Even stellar nurseries have lifetimes. Eventually much of the cloud will disperse. The dense reservoirs of gas will diminish. Star formation will slow. The landscape will transform. Yet the material itself will not vanish. The atoms will continue their journey. Some will become stars. Some will become planets. Some may eventually become part of the living organisms. The cycle continues, always moving, always changing, always creating something new from what came before. In many ways, that cycle is the deepest lesson hidden within the cosmic cliffs. The universe does not simply produce stars, it recycles them. One generation creates the ingredients for the next. Massive stars forge heavy elements. Supernovae distribute those elements. Clouds gather the material. New stars emerge. Planets form. The process begins again. Everything connects. The sun emerged from an earlier generation of stellar activity. Earth emerged from material created by ancient stars. Life emerged on Earth. Eventually, living creatures developed the ability to ask questions, to build telescopes, to study the sky, to look across thousands of light years and investigate places like the cosmic cliffs. There is something quietly remarkable about that chain of events. A cloud becomes a star. A star creates elements. Elements become planets. Life appears. Life develops curiosity. Curiosity builds instruments capable of looking back toward the clouds where stars are born. The universe, in a sense, becomes aware of its own history. Perhaps that is why images like the cosmic cliffs resonate so strongly with people. Not merely because they are beautiful, not merely because they reveal fascinating science, but because they connect us to something larger, a process stretching across billions of years, a process that helped create everything familiar, the stars above us, the world beneath us, even ourselves. And so, as our journey through the cosmic cliffs comes to an end, the nursery itself continues its work. Hidden stars continue growing inside the dust. Radiation continues sculpting the landscape. Future solar systems continue taking shape. The great cycle continues exactly as it has for billions of years. Patient, persistent, unhurried. The universe is in no rush. It never has been. And somewhere far beyond Earth, beyond the familiar constellations, beyond the reach of ordinary sight, the endless birthplace of stars remains quietly at work, preparing futures that have not yet arrived, creating worlds that do not yet exist, and continuing a story that is far older than humanity and far from finished. For now, though, this is a good place to rest. Thank you for spending this time among the cosmic cliffs with me. Wherever you are listening from tonight, I hope you've enjoyed this gentle journey through one of the most extraordinary stellar nurseries ever observed. And as you settle a little deeper into comfort, perhaps let your thoughts drift slowly outward one last time, toward those distant clouds, toward those hidden stars, toward that immense landscape of gas, dust, gravity and time, still creating, still evolving, still waiting for the next generation of stars to emerge from the darkness. Good night, sleep well, and I'll see you on our next journey through the universe.